Dari keinginan pemerintah Indonesia untuk memenuhi kebutuhan sumber daya manusia di luar Pulau Jawa, berdirilah sebuah perguruan tinggi negeri di jantung kota Balikpapan bernama Institut Teknologi Kalimantan. Diresmikan oleh Presiden Republik Indonesia ke-6, Susilo Bambang Yudhoyono pada tanggal 6 Oktober 2014, Institut Teknologi Kalimantan memulai kegiatan akademik dengan menerima mahasiswa baru sejak tahun 2012. Dan terhitung sejak 5 September 2019, jumlah mahasiswa Institut Teknologi Kalimantan adalah sebanyak 4.074 mahasiswa. Desain infrastruktur, pengelolaan sumber daya air, dan manajemen proyek konstruksi dipelajari dalam program studi teknik sipil. Identifikasi potensi masalah wilayah dan kota, serta menyusun rencana tata ruang didalami dalam program studi perencanaan wilayah dan kota. Pada program studi matematika, selain mempelajari aljabar, geometri, dan analisis, matematika juga berpeluang untuk mempelajari statistika, komputasi, aktuaria, dan riset operasi. Institut Teknologi Kalimantan juga menginginkan lulusan yang dapat berperan menjadi konsultan dan sistem integrator, database specialist, dan IS academician yang dilatih dalam program studi sistem informasi. Prodi Informatika mempelajari bidang dasar informatika, pemrograman komputer, serta mampu mendayagunakan, mengevaluasi, dan mengidentifikasi pengembangan sistem berbasis komputer. Tergabung dalam jurusan Sains, Teknologi Pangan, dan Kemaritiman, program studi Fisika, Teknik Perkapalan, dan Teknik Kelautan, bersama mengembangkan sumber daya manusia melalui mahasiswanya dengan mempelajari sifat-sifat fisika yang ditujukan untuk mendukung industri, konstruksi dan kekuatan, hidrodinamik, dan sistem perkapalan, hingga kemampuan dalam merancang, mengembangkan, dan menganalisis struktur bangunan lepas pantai. Institut Teknologi Kalimantan juga mencetak mahasiswa yang memiliki kemampuan di bidang konversi energi, industri pertambangan, manufaktur, robotika, dan otomotif melalui program studi teknik mesin. Mahasiswa yang memiliki peluang kerja pada bidang kelistrikan yang mencakup pembangkit tenaga listrik dan sistem jaringan distribusi melalui program studi teknik elektro. Proses dan cara mengubah bahan baku atau mentah dan bahan kimia menjadi sebuah produk komersial dengan memanfaatkan proses-proses kimia maupun perubahan sifatnya dipelajari pada program studi teknik kimia. Lulusan teknik industri mempelajari bagaimana cara merancang, menganalisa, mengaplikasikan, dan mengintegrasikan beragam faktor industri yang mampu bekerja dalam bidang operation, quality control, hingga industrial manager. Tergabung dalam jurusan ilmu kebumian dan lingkungan, program studi teknik material dan metalurgi mempelajari tentang sifat mekanik, fisik, dan kimia bahan logam, komposit, plastik, dan keramik, serta aplikasinya terhadap berbagai bidang. Sebagai dedikasinya terhadap lingkungan, Institut Teknologi Kalimantan membuka teknik lingkungan yang mempelajari semua penyebab permasalahan di lingkungan, mulai limbah padat atau sampah, bahan berbahaya dan beracun, B3, hingga limbah laut. Sebagai wadah pengembangan diri mahasiswa, Institut Teknologi Kalimantan menyediakan unit kegiatan mahasiswa di antaranya Asma Warma, BICAME Enggang, futsal, basket, tenis, voli, badminton, seni budaya, kopma, fokus point, ITK musik, paduan suara mahasiswa ITK, Volks, Pramuka, Gangga Yaksa, Developer Student Club, Spekta untuk sang pencipta dan Bumetam.
Mungkin waktu kan kembali. Hadapi semua sedih. Kembali menjalani matahari datangkan pagi. Tak apa yang kan ku hadapi, semua ku nikmati. Dengan melodi yang menjadi ini, nadaku melayang terbang tinggi. It's true love, don't fake it. You better not, you better not. It's right here, don't waste it. You better not. When I'm up late and lonely, and I'm just out of pain, know what I wanna hear from you. When the doubt pulls me under, and I need to recover, know what I wanna hear from you. Say, baby, say to me the words that keep me going. Yeah, I know you know. Say, baby, say to me the words that made me heal. I love the way they feel. You give me some of that, sweet, sweet talk. Give me some of that, sweet, sweet talk. You give me some of that, sweet, sweet talk. Say it again 'cause I need it. Sounding so good that you need it. Some of that, sweet, sweet talk. Give it to me, oh, love. You know that I need it. Sweet talk. Give it to me, oh, love. You know that I need it. Sweet talk. Not gonna get enough of that sweet talk, baby. Oh, love. That sweet talk. Whenever she comes around, whenever I hear that sound, I feel like a millionaire. I feel like a millionaire. Whenever she comes around, whenever I hear that sound, I feel like a millionaire. I feel like a millionaire. Whenever she comes around, whenever I hear that sound, I feel like a millionaire. I feel like a millionaire. Whenever she comes around, whenever I hear that sound. Come on. I feel like a millionaire. Whenever she comes around, whenever I hear that sound. Smell like money when she walk by. All heat, no smoke, but she on fire. If Ain't suicide doors that she don't ride. She got the passport pussy or she don't fly. No lie. She gon' make you pay to see her work it. She only twerking for a bucket. Gotta see if shorty worth it. She must be the money. I feel like a millionaire. I feel like a millionaire. Whenever she comes around, whenever I hear that sound, I feel like a millionaire. I feel like a millionaire. Whenever she comes around, whenever I hear that sound. Morning, selamat pagi.
Selamat pagi. Good morning, Professor.
Morning.
Are you Lucy?
Oh, I'm the MC.
You're the MC. Okay.
Yes, for today. I think Miss Lucy is already here. So let's check this out. Okay, Bapak Ibu semuanya, are you in the room already? Yes. I would like to
Yes.
remind you to set your background as we suggested in the email for the participants and also the presenters, because we're going to start the conference real soon.
MC, what do we need to do with the background?
We are going to set it as in the email, Professor. So
Oh, okay.
I believe you you have already received the virtual background already?
I got an email from the 7th of September, and it mentioned that we use Zoom as the platform, time, meeting ID, passcode.
Oh, if you haven't received
but the
virtual background is not there. It's okay, Professor.
All right.
It's okay for you because it's actually for the participants to deliver their presentation. Yeah.
All right.
Okay. Should we begin, ladies and gentlemen? Okay. Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. I'm Healthy Susanti on behalf of LPPM and also the organizing committee. So today's conference became the third. It's actually held by the LPPM and also the organizing committees from Institut Teknologi Kalimantan. So I would like to also hold for honorable greeting for our presenters, for our attendees and guests, as well as our rectors and vice rectors who come and join with us in the Zoom room today. So our Excellency Professor Budi Santoso, thank you for joining with us today. And also Ibu Nurul Widyastuti as our Vice Rector of Academic Affairs. Welcome, Ibu. Thank you for coming. And also for attendees, I hope that you are okay and healthy in this pandemic, and I hope that you can just get through the conference very nice and smoothly. Today's conference, the third BICAME, Borneo International Conference in Applied Mathematics and Engineering, has a special theme, ladies and gentlemen. So our theme today is energy transition, smart technology and environment, and for sustainable development. I would like to also give special greeting to our keynote speakers today. First, Professor Robert Thomas Bahman from University Kuala Lumpur. Welcome, Professor.
Hello.
Thank you for joining with us, finally. Okay, and the second will be Professor Lydia Helena Wong from Nanyang Technological University. Professor Lydia, welcome to our conference today. And the last will be Dr. Aditya Farhan Arif from PT Rekayasa Industri. Okay, thank you, Dr. Aditya, for finally joining with us today as well. Before we pursue to the next agenda, I would like to invite all the attendees to stand up because we are going to play our national anthem, Indonesian national anthem, Indonesia Raya. You may have your position by now. Yeah, okay, let's just lift. You may start your playlist. Thank you.
Indonesia, tanah airku, tanah tumpah darahku. Di sanalah aku berdiri, jadi pandu hidupku. Indonesia, kebangsaanku, bangsa dan tanah airku. Marilah kita bersatu, Indonesia bersatu. Hiduplah tanahku, hiduplah negeriku, bangsaku, rakyatku semuanya. Bangunlah jiwa yang patuh, badangan untuk Indonesia Raya. Indonesia Raya, merdeka, merdeka, tanahku, negeriku yang ku cinta. Indonesia Raya, merdeka, merdeka, hiduplah Indonesia Raya. Indonesia, tanah yang mulia, tanah kita yang kaya. Di sanalah aku berdiri untuk selama-lamanya. Indonesia, tanah pusaka, saka kita semuanya. Marilah kita menjaga Indonesia bahagia. Tanah yang subur, jiwanya, bangsanya, rakyatnya semuanya.
Halo, halo. Halo.
Untuk Indonesia Raya. Indonesia Raya, merdeka, merdeka, tanahku, negeriku yang ku cinta. Indonesia Raya, merdeka, merdeka, hiduplah Indonesia Raya. Indonesia, tanah yang suci, tanah kita yang satu. Di sanalah aku berdiri, jaga hidup sejati. Indonesia, tanah berseri, tanah yang aku sayangi. Marilah kita berjanji, Indonesia abadi. Selamatkan rakyatnya, selamatkan putranya, pulaunya, lautnya, semuanya. Majulah negerinya, majulah tandinya, untuk Indonesia Raya. Indonesia Raya, merdeka, merdeka, tanahku, negeriku yang ku cinta. Indonesia Raya, merdeka, merdeka, hiduplah Indonesia Raya. Indonesia Raya, merdeka, merdeka, tanahku, negeriku yang ku cinta. Indonesia Raya, merdeka, merdeka, hiduplah Indonesia Raya.
Okay, thank you, Bapak Ibu semuanya, ladies and gentlemen. You may have your seat by now. Okay, we pursue the next agenda, we would like to also invite praying delivery by Mr. Gufron. Mr. Gufron, you may have your room, please. Thank you.
Yes, ready.
You may start, Mr. Gufron.
Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Ladies and gentlemen, let us bow our head for a moment, pray to God Allah Subhanahu wa Ta'ala, so that our international conference can be precious to all of us. I will lead this prayer based on the teaching of Islam. In those who are not Muslim, you are free to pray according to each of your beliefs. A'udzubillahi minasyaitonir rajim. Bismillahirrahmanirrahim. Hamdan yuwafi ni'amahu wa yukafi'u mazidah. Ya Rabbana lakal hamdu kama yanbaghi li jalali wajhika al-'azim wa sultanik. Walhamdulillahi rabbil alamin. Oh Allah, today on the day September 9, 2020, we gather here in Borneo International Conference of Applied Mathematics and Engineering. Oh Allah, make this international conference as a useful science assembly, as a medium of sharing useful ideas, knowledge, and experience of scholars, researchers, and students of various disciplines. May the conference we organize today benefit to our life. May the conference we organize today benefit to our life, broaden our knowledge, science, our ideas, and lead us to be successful, productive person, which in turn will boost dignity of our nation. Allahumma ikdi hajatina ya Allah, jihadana tablighuna da'awatana kasbana. Amwalana arzaqana ta'limana ma'alufi wal afiyah wassalamah wal manfa'ah wal barakah wal najah. Rabbana atina fid dunya hasanah wa fil akhirati hasanah wa qina adzabannar. Subhana rabbika rabbil izzati amma yasifun wa salamun alal mursalin walhamdulillahi rabbil alamin. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam
warahmatullahi wabarakatuh.
Thank you for the praying delivery, Mr. Gufron. We do hope that all this agenda is running smoothly. So before we begin our first main agenda to plenary session, I would like to invite speakers for the opening speech. The opening speech, the first will be delivered by the chairman of the third BICAME, Ms. Elindia Savitri. Ms. Elindia Savitri is actually a member of LPPM and also one of our lecturers of Institute Teknologi Kalimantan, majoring in urban and regional planning. Ms. Elindia Savitri, you may have your room, please.
Okay, thank you, Ms. Susan, for the opportunity. The first that we respect, Rector of ITK, Profesor Insinyur Budi Santosa Purwakartiko, PhD, Deputy Rector of Academic Affairs, Mrs. Nurul Widyastuti, SSI, MSI, PhD, Deputy Rector for Non-Academic, Mr. Dr. Muhammad Masyuri, MT, and keynote speaker, Professor Dr. Robert Thomas Wehman from University Kuala Lumpur, Malaysia, Professor Lydia Helena Wong from Nanyang Technology University, Singapore, and Dr. Aditya Farhan Arif from Manager of New Investment at PT Rekayasa Industri, and lecture within ITK, Institute Teknologi Kalimantan, contributing author, all guests from another university, all students, and ladies and gentlemen. Assalamualaikum warahmatullahi wabarakatuh. Good morning, presents to Allah Subhanahu wa Ta'ala, this given that has given favors and give in this morning. Welcome to this third international conference on Borneo International on Applied Mathematics Engineering as BICAME 2020. I'm blessed to join you here today. Maybe from you, ladies and gentlemen, you already know that the BICAME conference is an international conference that is held every 2 years and is organized by the Research and Community Service Institute Teknologi Kalimantan, IKLPPM. And for this year, BICAME has entered its third series, which is held today, 9 September 2020. And it's very special because it is done virtually due to the pandemic that is happening around the world. The theme of this year BICAME is energy transition, smart technology, and environment for sustainability development. This conference gathers scientists, engineers, practitioners, and other researchers who are active around the world and has been participated by 13 universities. Those are Gunadarma University, Halu Oleo University, Institut Teknologi Kalimantan, Institut Teknologi 10 November, Kairun University, Politeknik Penerbangan Surabaya, Sekolah Tinggi Teknologi Migas, Tribuana Tunggadewi University, Gajah Mada University, Indonesia University, Universitas Indonesia, Universitas Jember, University of Patria Arta, and University of Surabaya. For information, this conference has attracted 45 papers, but from the total of the submitted papers, this conference has accepted 37 papers. All selected papers will publish in EOP Conference Series, Journal of Physics and Transtech publication. And our thanks go to the third BICAME 2020 participants who have made a full contribution in engaging in idea and giving input on the research that has been done to develop science and knowledge for future progress. I also give thanks to the organizer committee, session chair, reviewers, and sponsor who have contributed to the success of this event. We hope in the future this conference can take more participants from around the world. Last but not least, I hope that today BICAME third conference will be done well, be useful, and hopefully we will all be healthy and protected by God. Thank you. Wassalamualaikum warahmatullahi wabarakatuh. I return to Miss Susan. Thank you.
Thank you, Miss Elindia. Okay, we're going to go to the next opening speech. I would like to invite Professor Budi Santosa to give the second opening speech to open this conference. Prof. Budi, you may have your room.
Excuse me. Yeah, good morning, everybody.
Good morning.
Good morning, the honor speakers, Professor Robert from University of Kuala Lumpur, Professor Lydia from Nanyang Technological University, and Dr. Aditya Farhan from PT Rekayasa Industri. Welcome to BICAME ITK third conference. Even though this is the virtual event, I am proud of the organizer committee of doing this third conference at a series of annual conference done by our research center, which every year doing this conference, 1 year for pengabdian masyarakat or community development, and then for the next year is for research. So this idea is very good because we have two big stream in our Indonesian lecturer job. Beside of teaching, we have to do research and we have to do community development. So every work that done by our lecturer should be contained in some scientific paper. So we're doing this two conference to contain this works done by our lecturer in Indonesia. Welcome to all participants in this conference. Even though this conference is not as big as the previous one, but we still can do this conference in the middle of the COVID pandemic. Yeah, in this year, the topic or the theme of our conference is energy transition, smart technology, and environment for sustainable development. Okay. This topic mostly cover our expertise in our institute. So for those who are not familiar with our institute is built on 2012, around 3 years. We are in the same location with Institut Teknologi 10 November Surabaya. So our ITS is like our mother, and then ITK, Teknologi Kalimantan, is the child of ITS. So after 3 or 4 years in ITS, and then we moved to Balikpapan, and we stand alone as a university, which is focused on science and engineering. So we have 17 study programs, which mostly are science and engineering. But in next year, we plan to build a new study program, what we call design komunikasi visual, which is maybe most dominant in art. Yeah, and the idea of building ITK is our government wants to build science and engineering universities in the other island rather than Java Island, because we have ITB and ITS, both are in Java Island. So government want to spread the education of science and engineering in other islands rather than Java Islands. So our government built ITK and ITERA, one in Kalimantan or Borneo and one in Sumatra Island. Okay. Up to now, we have about 3,000 students, and we have about 150 lecturers. So we are still young, yeah, compared to the other universities in Indonesia. So this year we are 6 years old, so we don't have many facilities or works, scientific works, relative to the other university in Indonesia. So this implementation or this conference, I think, is very good effort to build a scientific atmosphere in our university, so our lecturer can present their works in their academic works, and we can maybe through this conference we can build our relation or networking or collaboration. So in the next future year, our lecturer can make collaboration with maybe lecturer from University of Kuala Lumpur, from NTU, or maybe Rekayasa Industri and other universities in Indonesia. And now our government launched what we call as Kampus Merdeka, Merdeka Belajar, which enable us to make more collaboration, and that will be valued as credits, so it can replace some subject in some departments, so students don't need to take all subjects in the class or in the campus, but they can do some works in other campus or outside the campus. This is very good progress in our higher education. So when the students finish their studies, they will comprehend a lot of skills rather than academic skills. Okay, I'm not too long to give this speech. So by mention Bismillahirrahmanirrahim, in the name of God, which this conference I open officially. I hope this conference will be in good process, and everything will be okay. No certain what constraint or barriers. So it will last fluently until the all the agendas. Okay, thank you. And then again, welcome to this conference and enjoy the conference. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Prof. Budi, for the opening speech. Now, ladies and gentlemen, we finally open the conference. But before we go to the next agenda, I would like us, all of us, I invite all of you, ladies and gentlemen, Bapak Ibu semuanya, to have group photo. So for this, please open your camera and be ready for the best expression for today. Smile on our face. Okay, Mr. Committee, are you there? Is everything ready for us to take picture? Mr. Gilfi, maybe? Can you give sign for us?
We are ready for taking pictures.
Yeah, okay.
We count. 1, 2, 3. Say cheese.
Cheese.
Okay.
One more.
One more. Okay. Bapak Ibu, maybe you have a different expression, maybe with your hand gesture, for example, victory or anything. From Teknologi Kalimantan, people, pejuang, ladies and gentlemen, maybe you can use pekta. We can use pekta. Anyway, okay. Mr. Gilfi.
Yes, I will count. 1, 2, 3. Say cheese. Okay, thank you, Mr. Susan.
Thank you, Mr. Gilfi. That was awesome. I like this photo picture, actually, photo group. We're going to share it with you, ladies and gentlemen, later. All right. Without further ado, I would like to go to the plenary session. So before we go to plenary session, I would like to introduce to our moderator today. The plenary session will be led by Dr. Happy Aprilia. Dr. Happy Aprilia is a graduate of National Cheng Kung University, Taiwan. She just graduated from NCKU. She is really active as a researcher. She is from electrical engineering program. Her current project is about intelligent forecast and analysis technique for renewable energy system. All right, Ibu Happy, I would like you to invite in the room. The time is yours.
Thank you, Ms. Susan. Good morning, everyone.
Good morning.
Good morning.
Okay, I'm honored to be the moderator of this plenary session. But before we begin, I need to inform the attendees about the regulation that we need to follow in this plenary session. For your information, in this session, we accommodate the questions on the chat box, both in Zoom or in YouTube. So please do not activate your raise hand or open mic in the Zoom, okay? And also for another information is, please don't forget to fill the participation list. Okay, so let's start our plenary session. The first keynote speech is from Professor Robert Thomas Bahman from University Technology Malaysia. So before I let Professor Robert to give the speech, let me introduce his CV first. Okay, let me share my screen. So here is the short biography of Professor Robert. He has his PhD degree from Sheffield University, UK, and also he's a his bachelor degree is got from Wismar University, Germany, and then complete his master degree in Sheffield University, UK. So before he start his academic role in University Technology Malaysia, he's already working as a scientific officer at Crotoy Research Institute, UK, and also do some training, co-supervising postgraduate students, operating analytical equipment, such as AAS, ICP-MS, TGA, FTIR, as well as optical microscopes while conducting research. And then in his academic job as a professor, he already supervised like 100 undergraduate students,
Ardi, udah.
20 master students, and 8 PhD students.
Ketemu siapa?
And then like here, he is awarded as the Anugerah Pendidik Terbilang Mara as a Distinguished Educator Award, and his team won several prizes for Best Poster, Paper, and Presentation Awards. And he's also a panel member to assess the fundamental research grant proposals and examine master and PhD from several universities, such as Nottingham University Malaysia campus, Punjab University Pakistan, Anna University India, and also University Putra Malaysia. And here is some of his achievement as the Professor Malacca in Malaysia. And okay, that's all. A brief introduction of him. So, ladies and gentlemen, please welcome Professor Robert Thomas Bahman. Professor Robert, the room is yours.
Thank you. Can you see my screen, my PowerPoint?
Not yet, Professor.
Not yet.
Yes.
Let me share again. So,
yeah, it is clear.
So, okay. So many thanks to the MC and the chairwoman for the kind introductory words.
I would also like to express my gratitude to the organizers of the conference for inviting me as a keynote speaker to the 3rd International Conference on Applied Mathematics and Engineering. The initial plan was to come to the Institute Technology Kalimantan and present in person, but COVID-19 has had other ideas. In hindsight, it is presenting us with an opportunity to run conferences more sustainably with a much lower carbon footprint, if you consider the traveling, the customary goodie bags, and the rental of air-conditioned conference halls. Do you agree? Okay, before I start with my presentation, I would like, with your kind permission, to give a very brief overview of my university. UniKL, like Institute Technology Kalimantan, is a young university. We were established 18 years ago, so we are like the older brother, perhaps. UniKL is a campus university, and we are spread alongside the west coast of Peninsular Malaysia. Each campus represents a specialization such as automotive, marine, aviation, electrical, mechanical, and chemical engineering technology. We offer diploma, bachelor, master, and PhD programs, and all in English. I work for UniKL's Malaysian Institute of Chemical and Bioengineering Technology since the year 2007. This year, we managed to break into the Times Higher Education top 1,500 universities worldwide. So we are very proud of this achievement, and perhaps through collaboration with the Institute Technology Kalimantan, we can also achieve the same for Ithaca. Okay, let me turn your attention now to the actual presentation. When I received the invitation and saw the theme of the conference, I have decided to use this opportunity and platform to cover a topic that is close to my heart and of great importance to our future, the circular economy. The first 14 years of my life, I grew up in East Germany, an economy deprived of most natural resources. So, value preservation, reuse, improvisation, and recycling were very much our way of life. After the reunification, the sky seemed the limit. Everything was available in seemingly abundance, as long as you had the money, of course. However, not too long after the reunification of East and West Germany, a new topic started to emerge, the circular economy, of course. Not all was as rosy as it seemed with West German economy. That was also the time I decided to study environmental engineering. The topic of circular economy was, however, not as new as I thought back then. Based on a literature search in Google Scholar, the circular economy term was arguably first mentioned in 1972 by Professor Kenneth Boulding, who is an English-born American economist, educator, peace activist, and interdisciplinary philosopher. So that was before I was born. Interest in the topic has remained modest in the academic circle, as you can see on the figure, and it only started to really take off after the millennium. Now, more than 5,000 publications have been dedicated to the circular economy, and the numbers are still rising. What is behind the increased interest in this topic? I have phrased my presentation with the following question: the circular economy, a flight of fantasy or necessity? No. In order to answer this question, I would like to introduce you to the circular economy concept by asking some of the 5W1H questions. What is the circular economy? Why should we concern ourselves with the circular economy? Who should be involved, and how can the circular economy be achieved? So let's start with our first question. What is the circular economy? In a nutshell, the circular economy is an economic model in which materials, the building block of all products, are kept going in cycles within the economy. The cycles can be short, medium, and long-term, as shown in the diagram. As I hinted earlier, the idea of a circular economy is not entirely new. As a matter of fact, elements of the circular economy can be found in most, if not all, ancient civilizations. The photo here shows a metallurgical center in Dubai, in which broken ceramic and metallic objects were refashioned into new tools, weapons, decorations, and so on. Ancient Romans were not only expert soldiers and civil engineers, but also good at collecting, sorting, and selling certain refuse, as archaeological excavations have revealed. However, our ancestors were by no means ecological saints. They too polluted already their surroundings through mining, burned down or cut off entire forests to build ships, and created massive amounts of waste. Jared Diamond, an American geographer, historian, anthropologist, ornithologist, and author of the book Collapse: How Societies Choose to Fail or Succeed, identified 5 factors that contributed to the collapse of various historical societies, such as the Greenland Norse, the people of Easter Island, the Polynesians of Pitcairn Island, the Anasazi of southwestern North America, and the Maya of Central America. The most frequent factor was environmental damage, followed by climate change, hostile neighbors, society's response to environmental problems, and loss of trading partners. So there's quite a bit that we can learn from those failures. The circular economy has also been mentioned by Professor Winter back in 1989 as part of 4 phases of the relationship between mankind and nature. These phases may be regarded as an historical series, as I show here for the Western Europe, but they can also be found among currently existing societies at various stages of development. The first phase, the man uses nature while allowing nature the material, spatial, and temporal possibilities for self-regeneration. Phase 2 is looking at the exploitation which is of nature, which is based on a mechanistic conception of nature and a belief in its fundamental manipulability. This orientation leads to an enormous waste of new renewable energy sources, an artificialization of nature, as chemical products are employed, such as fertilizers and pesticides, and finally, the utilization of nature as a huge depository for pollutants, which are toxic and degrade little or very slowly. In the third phase, as a result of severe environmental pollution affecting everyone, young and old, rich and poor, rulers and citizens alike, environmental protection laws were introduced to control industrialization and exploitation of nature. The concept of what is safe to breathe, eat, and drink was introduced in this phase, as well as the idea of using the best available technology, not entailing excessive cost to minimize environmental damage. And the phase that we are, according to Professor Winter, now entering is the phase about thinking of new solutions. So here, Professor Winter focused on the need for more sensitive tolerance limits. Here he's talking about the lethal doses, 50, that is currently used to assess how dangerous a chemical is, and change that value to a test that looks at the well-being of test organisms. The use of technology that strengthens the useful natural forces and substances, which is reversible when mistakes become apparent, which is tolerant of failure, which takes the possibility of human error into account, which utilizes substances and energy sparingly, and which recycles instead of allowing emissions permanently to escape. Okay, now let's take a closer look at the why question. Why should we concern ourselves with circular economy? To kick it off, I will use the growth of microorganisms in batch culture as an analogy to mankind's growth on planet Earth. We will then be looking at headlines in the news related to pollution, followed by a closer look at the origin of pollution, which starts by mining non-renewable materials and conventionally ends with the disposal of products at the end of their life cycle. In order to further drive home why we should concern ourselves with the circular economy, we are going to look at the current extraction rates of minerals, the impact it has on humans and nature, and the fact that these minerals will be gone one day. So in answering the why we need to talk about circular economy question, let us look at the growth of yeast in a batch culture shown here in this slide. Some of you may already are familiar, others are not. At the beginning of the growth, there are only a few yeast cells in the nutrient solution. So when you look at the Erlenmeyer flask on the left, you see the very clear golden color solution. Food is plenty, pollution does not exist. Life is great for the yeast. As time goes by, the yeast cells multiply, the concentration increases. So when you look at the second Erlenmeyer flask, you start to see it becomes cloudy. In the graph that we can plot to show the concentration versus time, this is reflected in an exponential growth phase. If we wait a few hours more, our yeast is going to enter the third phase, the stationary phase. So this is C here. Growth is limited by the availability of food and the accumulation of toxic waste. Eventually, the yeast population starts to climb. We are in the last phase, phase D, the death phase. To some extent, our life on planet Earth faces the same kind of constraints as faced by the yeast in that Erlenmeyer flask. The resources we rely on are finite. Some may be renewable, some are not. Many of our activities generate waste, which, if we are not careful, accumulate in the environment and affect our life quality directly or indirectly. To further exemplify that, let me show you some news clippings from Malaysian newspapers that I collected since I moved to Malaysia in 2007. So there were reports about residents complaining about fuming stench from a nearby illegal land dump site. High lead content in river fish. The release of carbon dioxide into the atmosphere causing global warming. Companies being fined for causing pollution. Ministers in Terengganu enforcing stricter rules for bauxite mining because the mining companies polluted the environment. And quite lately in Johor, company dumped toxic waste into the river, and the fume that was released from the waste affected old people as well as children in the hospital. So we can see that pollution is still a big problem. Pollution is real and it affects many humans. It also shows that the government plays an important role by bringing the perpetrators to justice. So where does the pollution come from? As we have seen, environmental damage is still happening, and it is caused whenever a commodity is produced or consumed. What are commodities? Commodities can be classified into food, fuel, and materials, with materials further categorized into renewables and non-renewables. Renewable materials are derived from nature. So you see examples such as cotton, sheep wool, tobacco, wooden planks, veneer, and paper. Non-renewables are crude oil that is used to produce synthetic fibers and plastic products, primary metals that are needed for steel, aluminum, and alloy manufacturing, and minerals are used to produce cement, NPK fertilizer, and plasterboard, for example. So we can see already that by reducing the wastage of food, fuel, and materials, we can reduce resource consumption and environmental damage. Not convinced? Let's have a look at my next slide. The figure I've prepared here shows you how each step in the conventional life cycle from extraction of raw materials to use and disposal creates potential pollutants. In order to extract, refine, manufacture, use and dispose, energy in the form of fuel and electricity is required. The generation of electricity, the production and combustion of fuels on their own also generates emissions, pollution. To produce electricity and fuel, resources are required that can be coal, oil, gas, or nuclear fuel. In addition, each step, extraction, refining, manufacturing, and so on, consumes materials when, after they have passed through the process, experience some losses because of drilling, cutting, abrasion, for example. They help for generating waste. So the slide that I'm showing you here represents a linear process, because what we are extracting something from the nature, and at the end of the life phase we are disposing the product into the environment. So this is very problematic from an environmental point of view, but also the very fact that most economies rely heavily on non-renewables. So as long as the non-renewables are still available in the ground, this process can go on, but one day they will be gone. So the figure shown here illustrates the amount of raw materials that have been consumed in the USA alone. And this goes back until the 19th century. The renewables are shown in white, blue, green, and black. When we compare 1900 with 2014, there are at least two striking differences. Can you spot them? The first difference is the amount of raw materials consumed in 1900, which was around 20 times lower than in the 21st century. The share of renewables was more than 50% of the overall materials, while now it is only 5%. The consumption did not increase smoothly. You can see there were ups and downs. World War I and II, as well as various economic crises, caused a temporary drop in the raw material consumption. The greatest increase in raw material consumption can be attributed to the construction materials such as cement, sand, glass, and steel. Lately, the amount of recycled metals has been increasing, while non-renewable organic experience a mild decline. This may indicate that the American economy is starting to undergo a gradual transformation towards a recycling, if not circular economy. So this one looked at the input of an economy, the raw materials that go in. How about the waste that is exiting our economies? Figure 7 illustrates the amount or type of waste that exits economies of Australia, China, Germany, Japan, and USA over a 50-year time frame. We can see that mining waste is the greatest, followed by construction and demolition, metals, glass, chemicals, plastics, timbers, and crop residues. In terms of absolute quantity, China generated the greatest amount of waste, followed by the US. However, this comparison is not really fair because China has a much larger population than US or Germany, for example. So if we take into account the population and work out the waste that is generated per capita, then the Australians generate by far the greatest amount of waste. The only country that did not seem to change its position here is Germany. From figure 8, we can see that the mining sites that are used for raw material extraction are concentrated at the west coast of North and South America, the Mediterranean region, Scandinavia, southern Russia, east coast of India, South Africa, southeast China, and along the coastal line of Australia. So whenever minerals are being mined, there's bound to be some effect on the ecosystem. And the problem is going to become more severe as we run out of high-grade mineral ores. As mentioned, the extraction of raw materials from the mines that are generating large amount of waste rocks and overburden materials cause natural habitat loss, fragmentation, and environmental pollution. As the high-grade mineral deposits become depleted, poorer sites are either re-employed or opened up. And this results in an even greater amount of waste being generated, which in turn increases the global footprint of the mining industry. To give you an idea, Figure 9 shows an open pit copper mine in South Australia. The actual copper mine is shown on the right bottom, while the waste dumps plus the tailings are shown on the left top. Please note that the area of the pit, the copper mine, is just 20% of the total mine. Environmental issues such as dust and acid mine drainage need to be tackled by the operator, while a plan must be in place to restore the mining site as close to its original state as possible once the copper mining becomes uneconomical. How about mining in Malaysia? This photo shows a tin mine in Perak, which has been in operation since 1907. Please note the size of the mining machineries, here the trucks at the bottom right. This gives you an idea of the size of the mine and the amount of work required during restoration. Earlier, I mentioned that mining also involves artisanal small-scale activities. How do these look like? So in figure 11, I show you a photo of an artisanal small-scale mining in Congo and Burkina Faso. So this kind of mining is uncontrolled, exploitative, health and safety risk, as well as highly polluting with no effort to rehabilitate the abandoned mines. An estimated 13 million people are involved in artisanal small-scale mining. It is an important socioeconomic factor for the rural poor in many developing nations, many of who have fewer options for supporting their families. This artisanal sector is supplying 20% of the global gold, 80% of the global gemstone, 20% of global diamond, and 25% of the global tin production. So when you buy jewelry for yourself or your sweetheart, you may need to ask yourself whether this is really necessary. If you cannot resist, try to buy from a shop that supports responsible mining. In terms of gold, coal, and iron ore mining, they are known to have the greatest impact on the land. Reducing the demand for coal, gold, and iron ore is therefore pivotal in order to preserve the land for agriculture and other beneficial long-term activities. How about climate change? Does the extraction of mineral commodities release greenhouse gases? Based on a study by Hedwig in 2019, the production of iron, steel, aluminium, and other metals contributed 10% of the total amount of greenhouse gases released back in 2015. This is closely followed by the production of cement, lime, plaster, and other non-metallic minerals, accounting for 9% of the global greenhouse gas released. So this again shows that as far as climate change is concerned, the construction and manufacturing industry and the end users of their products play a critical role. How about Malaysia? The main greenhouse gas emission contributors in Malaysia are the energy industries, the transport manufacturing industries, and industrial processes, waste and agriculture sector. Please note here in number 3, the solid waste disposal sites, and number 4, fugitive emissions from oil and gas operations. For number 3, if all households would reduce the food wastage and start separating their organic waste, we could reduce our greenhouse gas emissions by around 10%. For your information, back in 2009, the previous Prime Minister of Malaysia pledged to reduce the greenhouse gas emissions by 40%, which means separating our food waste alone could contribute 1/4 to that commitment. It is a low-hanging fruit, because it just requires a change in attitude and some support by local governments and waste management companies. To round off our discourse into the mineral extraction, consumption, and its environmental impact, let us look at minerals from yet another angle. Some minerals are more important than others. Disruption of their supply due to natural disasters, labor strife, trade disputes, resource nationalism, and conflict needs to be avoided to avoid severe economic and national security consequences. Supply can come in two forms: supply from natural source, the mines, or from within the system. If we want to reduce the various environmental impact of mining activities by minimizing risk on economy, national security, and war, we need to switch the economical model from the current linear to a circular system. What are these critical minerals that are of such a grave concern? So as far as the United States are concerned, they have 35 critical minerals comprising of bauxite, chromium, cobalt, lithium, potash, and rare earth elements, amongst others. They are critical to the USA, not only because of the reasons mentioned, but also because the natural reserves are beyond the American border. Moreover, as I will show you in the next few slides, some of these minerals have a reserve lifespan of a few years only, assuming the current consumption rate. The first mineral I want you to look at is bauxite. Bauxite is the raw material required to produce aluminium. Bauxite reserve lifespans are greatest for Jamaica, Indonesia, Vietnam, and Brazil. 11 out of 192 countries own 83% of the global bauxite reserves. Bauxite reserves in the USA and China, two of the biggest economies in the world, is only 3 and 10 years. So good international relationship with bauxite-rich countries is therefore vital if the current linear economic model is continued. If less profitable low-grade bauxite resources are utilized, bauxite is predicted to last for another 200 years. As mentioned earlier, in the use of low-grade ores, it comes with a price because the concentration of aluminium is low and the waste that we generate is much, much higher. In terms of lifespan, the situation is even worse for chromite because noticeable reserves are only found in 4 countries. 4 countries. The chromite reserve lifespan varies between 4 and 40 years. If we include low-grade chromite ores, then we can utilize chromium for another 340 years. So for all the other elements that I have prepared a slide, I'm not going into details. What I want you to look at is that in almost all cases, the minerals are concentrated in a few countries and have only lifespans ranging from a few years until a few hundreds of years. So considering that all minerals are non-renewable with typical reserve lifespans ranging from decades to millennia, I hope you can see that it is pivotal that a new approach is required, moving away from extraction towards keeping the material in our economies. By doing so, we do not destroy ecosystems or agricultural land, but we also reduce the risk of war for these critical minerals. In our next slide, we shall turn our attention to the next W question now. So who should be involved in the circular economy? Our neighbors, our children, the rich West? In my opinion, it takes the concerted effort of everyone. The parliament and government who can revise or draft new sustainability relevant acts, educational institutes like Institute Technology Kalimantan and UNIKL and NTU to include elements of sustainability thinking in their curricula and research activities. Engineers and engineering technologists to design processes and products with sustainability in mind. They have the skills to extend the lifespan of processes and products. And last but not least, every one of us aiming to pursue a more sustainable lifestyle. So how can we achieve the circular economy? The answer I have already given in general, but let us look at it in more detail. Let us start by looking at two examples we are familiar with, buildings and vehicles. How can we make them more resource efficient, long-lasting, and recyclable? The results of a study by Hedwig et al., in which trade-offs between material and energy use strategies in buildings have been investigated, are summarized in this table. The green colors show the most favorable strategy, while red is the opposite. For example, a building with a large floor area and room height that are occupied by a few people only requires a lot of material during the construction and repair phase, while the energy consumption during operation, for example, aircon and light, goes up too. So the most effective strategy are more intensive use, smaller units, reduction of cooled and heated areas, use of sensible temperature settings, and the reuse of materials. How about cars? Similar story. Driving around alone in big cars is material and energy intensive. The most impactful strategy involves sharing smaller, lightweight cars, which is both material and energy efficient. In my slide on who should get involved, we have seen that it takes everyone to be on board, including the parliament and government. So from a macro scale perspective, we need parliaments and governments to develop policies that incentivize changing patterns of vehicle use and shifting towards trip-appropriate smaller vehicles. We need to implement green public procurement, virgin material taxation, removal of virgin resources subsidies, and recycled content mandates. However, a word of caution here. From past experience, we have seen that monetary savings can lead to an increase in consumption in other parts. For example, savings from the use of peer-to-peer lodging can lead to more travel and greenhouse gas emissions. This is known as the rebound effect. So policy instruments that directly or indirectly raise the cost of production or consumption, such as taxes or cap and trade systems, can reduce the rebound effect. Other examples of green policy ideas include no tax on renewable resources, such as human labor. So that means your income tax, for example. Removal of subsidies from non-renewable resources, such as coal, and no GST or VAT on value preservation activities. Another idea would be to require companies to extend the warranty period for consumer goods and buildings. This will encourage companies to design products that last. What else can the business world do? They can start to sell goods as services. For example, rent photocopy machines. We can do more intensive usage, less product to provide the same service. For example, through a more space-efficient design of buildings or multifunctionality of gadgets, or use of a product at a higher utilization rate. Lifetime extension. So here, more service, after-sales service to maintain the product, and design lightweight materials. Before we get too excited and carried away, another word of caution. If we implement all the ideas, there are limits to the circular economy. So this figure here illustrates the recycling of a car that has come to the end of its life. You can see on the left that the body of the car is made of different materials. If we cannot perfectly dismantle the car into its various components, we end up with a mix of different materials. Technology exists to separate them. However, it is not perfect. It's not 100%. So that means when we melt the classified material, we are adding impurities, which in turn affects the properties of the new product. In order to keep the impurities at manageable levels, it is current practice to mix recycled material with virgin material. But as we know, the use of virgin material has two problems, because its extraction causes environmental destruction and it is a finite resource. Another issue is related to the losses that occur due to natural processes such as corrosion, erosion, and abrasion. So we cannot cycle everything perfectly. There are losses. So that shows that even when we move away from a linear towards a circular economy, there are limitations. Korhonen and his colleagues summarized at least 6 limits and challenges for the circular economy. They are thermodynamic limits, system boundary limits, limits posed by the physical scale of the economy, limits posed by past dependency and lock-in, limits of governance and management, and limits of social and cultural definition. The most fundamental limit is related to the second law of thermodynamics. So as we have seen, technological and natural processes result in loss of material or increase in impurities. So if we say that we cannot avoid these losses, we will sooner or later run out of these minerals, be it whether we cycle them or not. So this suggests that ultimately we are returning back to a system in which we rely almost 100% on renewables, like our ancestors did. There may be a solution to it, provided we have resolved the energy problem. From space exploration, we know a bit about the planets and other objects in our solar system. For example, there are asteroids out there like 16 Psyche that contain metals that could sustain our current economy for the next million years, based on estimates from NASA. NASA is planning a mission in 2022 with the arrival at 16 Psyche in 4 years later, 2026. Right now, space mining is not an economical option, but the cost of space travel have come down, as you can see on the right top, from $20,000 to $10,000 to $2,000 per kilogram. So I'm coming to the end of my talk. Instead of me summarizing, let me ask you, do you think, is the circular economy a flight of fancy or a necessity? Terima kasih, and thanks for your time.
Thank you, Professor Robert, for an interesting speech. So for the attendee, if you have any question, please write it down on the chat box, because I already see the question to Professor Robert. But, and also I'm sure that Professor Robert will reply it soon. But let's continue first to the second keynote speakers for today's plenary session. So our second keynote speaker is Professor Lydia Helena Wong from Nanyang University of Technology, Singapore. So before we begin her speech, let me introduce her biography first. So here, Professor Lydia Helena Wong is an associate professor and assistant chair research at the School of Material Science and Engineering, Nanyang Technological University, Singapore. Her research area include solution-based synthesis of thin film and nanostructured metal oxides, and also chalcogenides, photovoltaic devices, photoelectrochemical devices for solar to full conversion, and accelerated discovery of new materials using high throughput synthesis and characterization methods. And to date, she has published more than 130 publications, including reviews and book chapter in the international peer-reviewed journal. Professor Lydia also has served as editor for Journal of Material Science, Materials in Electronics in 2017 and 2019, guest editor for Journal of Materials Chemistry A, and also an assistant chair in 2015 till 2018. She is currently serving as the Managing Director Southeast Asia of Ikatan Ilmuwan Indonesia International. So here is some research interest of Professor Lydia, and she has many projects which are undergoing right now, and this is the latest publication of her. So to all attendees, ladies and gentlemen, please welcome Professor Lydia Wong. Professor Lydia, the time is yours.
Hello.
Hello.
Good morning, everyone.
Good morning.
I hope you all can hear me very clearly.
It's clear enough, Professor Lydia.
Okay.
Yes.
First of all, I would like to thank the organizer for inviting me to give this keynote speech. Actually, Kalimantan is a place that is very close to my heart because my mother was born in Kalimantan. And I was actually looking forward to come to visit you and to take a look at the place where my mother's family is from. But unfortunately, because of this COVID-19, this is not possible. But I hope there will be more opportunities in the future where we can collaborate because Singapore and Indonesia is actually very near. So today, maybe I will just start sharing my screen. Okay. Can you see my screen now?
Yes.
Okay, good. I think to make sure that the connection is stable, let me just, okay, give me a minute. Okay. Okay, wait, I need to. Okay. Okay. So the title of my talk today is on solution process materials for next generation solar cells and artificial photosynthesis. So we will move a little bit from the circular economy to renewable energy. I'm from NTU, and I think there's now the host has kindly introduced a little bit of my background. So I was actually already and I spent I was born and was raised in Indonesia until I came to Singapore to study. And just a little bit of introduction of NTU. So if you have a chance to visit Singapore, you will most likely land in Changi Airport. And then you can take the MRT all the way to the west, where you can actually visit us at NTU. Okay, next. So NTU was started in 1991, and at the moment we have around 34,000 student population and around 3,300 PhD students. Out of all this student population, 15% of the undergraduate or mahasiswa S1 is international. Ratio increases for master and PhD students. And we have around 1,007 full-time faculty members and around 1/3 are international professors. And then we also have around 2,350 research staff who are actually very crucial in supporting our research activity. And among all the rankings that NTU has, as one of the world's top 15 most beautiful campus by American Express Travel and Leisure magazine. So the campus is not only green by nature, but we also have installed solar panels on the rooftops 5 megawatt solar panel installation, which is the largest installation of solar panel in a single location in Singapore. And I think this audience does not need to be convinced that the threat of global warming is real. And this is not a hoax. Yeah. So basically, if the Earth temperature increases by 5 degrees C in 2100, in the year 2100, Jakarta, Singapore, and Beijing will disappear. So one way to make sure that this doesn't happen is to use renewable energy. And one of the most sustainable and abundant source of renewable energy is solar cell. And the reason why we choose solar is because the amount of solar energy emitted per hour on Earth's surface is enough to produce energy to supply the worldwide yearly energy demand. Or in other words, if you cover this area or the size of Sumatra with a standard solar cell, this will deliver the entire world's energy demands. So this is the huge potential of solar cell. Now, I think most of you are familiar with solar cell, which is made of silicon and deployed on the rooftop. But the research interest of my group is actually to develop solar cells beyond silicon, because if we only rely on silicon to be installed on rooftops, there will be problems, especially on dense cities like Singapore or Jakarta, where we don't have enough surface area, we don't have enough rooftop area to install solar panels. So for example, one possibility is to make a semi-transparent solar cell and install the solar panels as windows or facade. So this is an example of a bus stop in Melbourne, which utilizes transparent solar panels. Yeah, this picture is a courtesy of our company collaborator Clearview, which deals with heat rejection energy generation solar windows. So imagine in future if we can actually cover the entire buildings with solar panels, for example, as a facade, or this one as a door, or we can also install solar panels on rooftops of cars and also on agriculture in the greenhouses. So my own group focuses on developing technologies related to printable semiconductors. So we synthesize semiconductor inks, and modify its optical, electrical properties, then interfaces, as well as nanostructuring in order to make efficient solar cell or artificial photosynthesis. So in this talk, I will focus a little bit on two aspects. One is on solar cell materials, and the other is on artificial photosynthesis. The first material that I will cover is CZTS, yeah, or copper zinc tin sulfide. Now, this CZTS has a wonderful properties because it consists of earth-abundant element. Copper, zinc, tin, sulfur, selenite. I think most of this can be found easily in Indonesia. The band gaps of this material is between 1 to 1.7 EV, which translate to a theoretical power conversion efficiency of around 30%, which is comparable with silicon. And another benefit of this structure is that the band gap can be easily tuned. So by changing the composition of the sulfur and selenite, you can actually change the band gaps and tailor the power conversion efficiency of this material. Another benefit of this material compared to silicon is that it has a high absorption coefficient. So the thickness of CZTS-based solar cell can be 100 times less than silicon. And because of this, we can actually print CZTS on plastic or on flexible stainless steel substrate. And this will allow and open up opportunities for application as a building facade or window coating. Now, the problem with this material is even though the theoretical limit is around 30%, the best demonstrated solar cell efficiency is around 12 to 13%. And what is the reason for this? This problem are still under investigation, but many people believe that the problem lies with the difficult control of composition and phase and the natural tendency to form point defects, which is electrically harmful. So in the next slide, okay, this is, you don't have to look at this and try to understand this. To make the story short, this is a representation of the conduction band and the valence band of CZTS. And there are a lot of defects associated with copper, zinc, and tin within the band gap. And this causes the reduction of the power conversion efficiency. So the research questions that we are trying to address here is, can we have a defect-tolerant casterite? Yeah. And what is the origin of the defects here? If you look at the crystal structure of CZTS, this crystal structure consists of three cations, copper, zinc, and tin, represented by the blue and the green and the orange atoms here. The size of these three atoms are very similar to each other. So it is very easy for them to switch around within the crystal lattice. That's why these atoms are denoted with blue and green color at the same time. And when they intermix within each other, they created a lot of point defects. Yeah. So because of this, there is a high chance of formation of anti-site defects, and this translates to electrically harmful defects. Now, since the main root cause of these defects are the close size of this copper, zinc, and tin, okay, if you look at the periodic table, copper, zinc, so one way to solve this problem is to replace one or two of these elements with other atoms with a much larger or much smaller ionic size. So the probability of forming anti-site defects will be much less. So throughout the years, people have tried different strategies to do this. They have tried to replace copper with silver or lithium. They try to replace zinc with cadmium, magnesium, manganese, and barium, or replacing tin with germanium. There are also efforts in doping with different types of element, alkali metals, as well as antimony. And our own group has tried a few things by using manganese. Actually, our group is one of the first who reported manganese substitution in CZTS. And then we have also tried magnesium, cadmium, and also silver. In this talk, I will not cover everything. I will just give you the most recent example of our efforts in silver and cadmium. And how do we make the CIGS or CZTS solar cell is by using a solution process sequence. So this is something that is simple enough and does not require a lot of investment in large equipments. Some things that people with simple chemistry labs will be able to do. And I really like to share this with because usually they will be able to do it in their lab too. So we start with ink. Okay, so we use salt, yeah, copper, copper, indium or gallium, or copper, zinc, and tin salts dissolved in thiourea, an organic solvent, to create an ink. After that, we use this ink to spray or to spin coat on molybdenum coated glass, followed by an annealing in a furnace. Subsequently, we perform chemical buff deposition, and this is the apparatus. If you can see, this is only a beaker on a hot plate. And then the only vacuum-based deposition that we did is by using a sputtering to deposit transparent conducting oxide. And finally, we deposit metal contacts as the top electrode, and this can also be done just by using a silver paint. Yeah, so all of these are relatively simple to make. We try to reduce the defects in CZTS, a combination of both silver and cadmium at the same time. So in this particular work, when we make a CZTS, a pure CZTS, the efficiency is around 6 to 7%. When we substitute 5% of silver, the efficiency increases a little bit to 7 to 8%. And when we substitute with cadmium, the efficiency increases further to 8 to 9%. But when we combine both silver and cadmium at the same time, the efficiency actually increases to between 9 to 10%, and the highest is almost 11%. And the main reason why this silver and cadmium works marvelously in this material is because we found out that silver and cadmium pacificates different types of defects within CZTS. And that is the reason why our efficiency is improved. Most recently, we also made a fully substituted cadmium CZTS. And in this example, we actually found an evidence that by fully substituting zinc with cadmium, meaning we don't have zinc at all, we actually reduce the formation of tin-related defects, which is located deep in the band gap. And because of this, the photoluminescence of CZTS is much higher than CZTS. And this and a very sharp EQE band edge. And this is a signature of a much reduced band tails and reduced deep defects in CZTS. So it seems that this material is very promising for pursuing the research direction in CZTS. So just to give a perspective of a novel copper chalcogenide compound beyond CZTS, different groups have started to replace zinc with other metals with a much higher ionic structure. For example, with iron. So the highest efficiency in the world was around 2.9%. This is by a group in India, Professor Ajay Pal. And then when they replace zinc with barium, 5.2% efficiency is obtained by Professor Michi in Duke University. Silver can get efficiency around 5%. Germanium substitution is able to push the efficiency to 7.6%, but our cadmium substituted CCTS managed to get an efficiency of almost 8%. And I think the best part is that we have found an evidence that this really reduces the formation of defects. And we believe that there are a lot of potentials to be done with this material in solar water splitting as well as carbon dioxide reduction. So one recent example that we did with this material is to use this CCTS as a photocathode in a water splitting experiment, and we managed to produce hydrogen and the highest reported photocurrent for casterite photocathode. Now I will move a little bit to a different focus of our group. We also are trying to make semi-transparent solar cell for Windows application. So this is an example that we did with a CZTS solar cell. By reducing the thickness of the absorber, we managed to make a semi-transparent solar panels with CZTS. And the semi-transparent solar cell state-of-the-art using silicon are usually produced by creating a mosaic of a silicon solar cell on glass like this. So you will not be able to make a seamless semi-transparent solar cell using silicon. So this opened an opportunity for thin film photovoltaic where we can actually coat and control the thickness of our film uniformly across a large area glass panel. And actually, there are many possibilities here, especially in the CIGS or material and as well as perovskite. So in this diagram, actually what you see is the relationship between power conversion efficiency with transparency. So a high, when the transparency is zero, okay, if you see a typical solar panels, usually you cannot see because the transparency is zero. That means the solar cell absorbs most of the sunlight efficiently. And this will lead to the highest power conversion efficiency. As you thin down the thickness of the solar panels, you increase the transparency. But however, as you increase the transparency, the amount of solar energy absorbed will be reduced. And consequently, the power conversion efficiency also will decrease. So there's always an inverse relationship between power conversion efficiency and transparency. So one promising material that has quite a reasonable efficiency at high transparency is metal organic perovskite. And we try to do this by using a perovskite structure. So for those who are familiar with dye-sensitized solar cell research, perovskite is one of the hot materials that has emerged in the last 5 years also as the nicest dye in the dye-sensitized solar cell configuration. And by tuning the thickness of this perovskite, we managed to get an efficiency of around 15% for semi-transparent solar cell. We also try to create transparency by making a pattern using a polymer grid, and we are able to make a seamless semi-transparent solar cell made of perovskite. We also combine both CIGS and perovskite perovskite solar cell in a tandem configuration to create around 20% efficiency of a tandem cell. And this is one of the first report that managed to show this demonstration. So if you're interested to look into the publications on solar cell, you're welcome to take a look at these slides or just go to my Google Scholar to look at more details of some of our works. Now, in the second part of my talk, which I will only speak very briefly because of time limitation, I will touch on the concept of artificial photosynthesis. So many of us are familiar with the role of leaves in converting water and CO2 into oxygen and carbohydrate. So what we are trying to do is also try to replace this leaf with an artificial leaf, which upon dispersing into water and reacting with solar energy will generate oxygen to the environment as well as hydrogen, which can be stored in a hydrogen storage and used as a hydrogen fuel cells. How do we do this? It's actually very similar by using materials used for solar panels. The requirements for photoelectrodes are also very similar with solar cell. It has to have a good band gap, very high absorption coefficient, but most importantly, the band energy level should straddle the conduction, the water reduction level as well as the water oxygen level. And this is an example of a water splitting by photoelectrochemical cell. We can use the absorber either as a photoanode, which will produce holes that create oxygen, or we can use it as a photocathode, which will produce hydrogen. We have used different types of oxide as an anode, for example, iron oxide, etc. And also the castrite or CZTS that I discussed just now was used as a photocathode. One interesting material here, which I think you might be interested, is hematite or iron oxide. And this is actually rust. This is actually a karat besi, yeah. So you can actually find this very easily. And also I think if you manage to harvest rust from the this kind of structures, you will be able to produce actually to try to harvest the benefit of metal waste into a renewable, converted into renewable energy. So iron oxide actually has a good band gap for solar absorption, and it is also stable in a wide pH range, because when you do water splitting, you need to immerse this into water. So stability in a wide pH range is very important. And also it is abundant, cheap, and non-toxic. Okay, because basically this is a rust. Yeah, and the theoretical solar to hydrogen efficiency is quite near to 16%. So we have, however, this iron oxide has some disadvantages. Even though it has a good absorption coefficient, it has bad charge transport properties. So as a result, you cannot make a thin film hematite or iron oxide. You need to make it into a nanostructuring. And we have done this also using solution process. We make iron oxide nanorods. Okay, this is also done in the lab very easily using some chemicals. And over the years, we have done a few things to improve the performance of hematite, either by using a surface overlayers, tin oxide, titanium oxide, etc., using doping of manganese and tin, or using a co-catalyst to deposit on top of these nanowires. And we have also tried to make it into a large area demonstration. So this is the apparatus we have in the lab of a hematite illuminated with solar simulator. And we have also coupled the hematite photoanode with a solar cell. And here we are able to produce a solar to hydrogen efficiency of 3.4% using solar panel as the source of electricity. So to summarize, this hematite has a theoretical photocurrent of 12%, which will be translated into 16% solar to hydrogen efficiency. But at the moment, the highest reported photocurrent is only 6 milliamp per cm square. So there are a lot of room for improvement from 6 milliamp to 12 milliamp. And we believe that a couple of combination using hydrogen treatment, doping, and surface overlayers will be able to push this further into 12% efficiency. So the next thing that we did in our group is to use iron oxide and dope it with titanium to produce material which conduction band minimum and valence band minimum straddle the water reduction and oxidation reaction. I think to cut the story short, this is our first demonstration of iron titanate. We managed to make a single phase thin film. And then after that, we further improved this by combining it with hematite in order to make a heterojunction, which produce a suitable band gap for charge separation and extraction. And then finally, in the last few months, our group has been doing combinatorial synthesis and high throughput characterization of metal oxide and chalcogenide. So the purpose of this experiment is to print many different types of composition in a very short time. So we are able to screen which composition will give the best power conversion efficiency or solar to hydrogen efficiency. And that will allow us to reduce the research time. So we have done this by using an inkjet printing machine as well as scanning droplet cell system. And this is an example of the color map of a photoelectrochemical properties obtained from the SDC. So from this study, we found that the optimum current density is obtained when you dope the metal vanadate with 7% chromium. And then we choose this composition to make a. So if you're interested to look at our publication in artificial photosynthesis, you're welcome to take a look at this publication or just go to my Google Scholar. And this is one for those who are interested to look into new materials for solar cell. I invite you to look into this journal articles, which is available free. This is a compilation of world record in organic solar cell efficiency, which I compiled together with my colleagues from all over the world. And you are welcome to take a look. And finally, I would like to acknowledge my team members, without whom I would not be able to present all the work that we have done so far. So these are my latest group members. There are around 15 of us from 7 different countries, including Indonesia and Malaysia as well. And we also have a lot of good collaborators from all over the world, and also the funding agency. With that, I would like to thank you for your attention, and I'll be happy to take any questions. Thank you.
Thank you, Professor Lydia, for the interesting explanation about the solar panel research. So before we go to the question and answer session, let's welcome our third keynote speech from Dr. Aditya Farhan Arif, a manager in Rekayasa Industri Limited Company. So before we start the keynote speech, let me introduce a brief explanation about him. So here, is everyone see my screen? Okay, I guess so. So Dr. Arif is,
Yes.
okay. So Dr. Arif is 33 years old, a manager of new investment at Rekayasa Industri Limited Company. And he also serves as a visiting professor at Department of Chemical Engineering, Institut Teknologi Bandung, Indonesia. Received a Bachelor of Science and Master of Science in Chemical Engineering from ITB, and also a Doctor of Engineering in Chemical Engineering, Hiroshima University, Japan. He spent his time as a research assistant professor at Department of Chemical Engineering of Hiroshima University, Japan, and a visiting research at Department of Process and Mechanical Engineering, ETH Zurich, Switzerland. And the field of expertise of Dr. Arif encompasses synthesis and functionalization of nanostructured materials for energy and environment. He received several awards for his achievement in this field, including Hosokawa Grant for Promising Researchers at 2015, and an Outstanding Internal Contributor Award from the Society of Powder Technology, Japan, in 2019. He has given invited lectures at some institutions, such as ETH Zurich, TU Delft, Netherlands, and Gadjah Mada University, Indonesia. And it's shortened as like here. He co-founded the Indonesian Photocatalyst Society earlier this year. So let's welcome Dr. Aditya Farhan Arif. Dr. Aditya, the room is yours.
Okay, thank you very much, Ms. Happy.
Okay.
Hello, everyone. It is nice to meet you here in the virtual conference. Although the same as what have been mentioned by Professor Bachmann and also Professor Wong, that I would love to attend this conference physically myself and pay my first visit to ETK because I have some friends there. And so I would just like to start my screen share. I hope you've seen my slides already now.
Yes.
Okay, so I would like to take this opportunity to share our experience and our thought in surviving the death valley of technology, especially in terms of building or developing the sustainable energy for Indonesia. The topic that I'm bringing in right now is actually closely related with what have been elaborated by Professor Wong. So it would be nice if one day we can collaborate together to build next generation solar cell industry in Indonesia. So as earlier introduced by the moderator very nicely, I am basically a researcher who has an opportunity to manage the businesses of a state-owned enterprise. And this is the company that I'm working at right now, Rekayasa Industri, or abbreviated as Rekind. We are the only engineering procurement construction company owned by the government of Indonesia. We have some business units, including oil and gas, power mining, and petrochemical, but we are now also shifting our business, especially from the viewpoint of investment and research and development to the renewable energy. So our main job, we have one job from the government, that is to build the industry. And speaking of building an industry, I would like to highlight that building an industry is not as simple as constructing a factory. It's not the same as building a factory. When we build the industry, it's actually what we are doing is actually we are creating the industrial ecosystem consisting of the technology, the finance, the market, and the supply chain. Because this is an ecosystem, without one of them, it is impossible for us to make an industry. Possible for us to make a factory without market, for example, but it's impossible for us to create an industry. And I would say that technology plays an important role in the industrial ecosystem because it is the core of the industry. So if we develop the technology, we are basically developing the industry. And if the industry has been established, we roll the wheel of the economy, and at the end of the day, we are able to achieve the ultimate goal of the economy, which is prosperity. So it is clear that we have to develop technology. And we believe that technology should be uniquely developed for a specific region or country, because every region, every country has different characteristics and resources. We have one experience regarding this matter. We once purchased a license of technology from one big multinational company. This technology is used to treat sulfur, to recover sulfur from natural gas using a microbiological process. When we applied this technology in one of our projects in Indonesia, it turned out that the technology did not work well because the microbial agent could not survive the environment in Indonesia. So what we did back then is we combined the bacteria with the local culture. So this is one of the examples why we believe that technology should be uniquely developed for one country or one region. And the technology development is conducted through innovation. Innovation is a long journey, it's a long process, which takes us from research to the industry. And sometimes we fail in doing the innovation, tapping us into what we call death valley of technology. This is a condition where there is a mismatch between research and industry, so we cannot upscale the technology to the industry. We know that as researchers, we are talking about the future. We are preparing the world using science, and we are focusing on the lab scale. We are talking about the next 1 or 2 decades. But on the other hand, the industry is talking about business. The business is today. The business opportunity cannot wait for the technology to be ready sometimes. And it is unfortunate that in Indonesia, especially, most of the industry tend to purchase the technology that is already readily available in the market instead of putting effort in developing the technology from scratch. So that's why they don't want to fund the development of the technology. And this is unfortunate because we believe that technology should be implemented in the industry. Otherwise, it is useless. I would like to cite the late Professor Habibie, the former president of Indonesia, for this statement. And it is quite unfortunate as well that the government of Indonesia took this statement in a wrong way. They translated into a belief that every single research should be applied research. No, it's not. We do need basic researches because we do need to understand ourselves, our resources. So basic research is necessary. What important is that we need, I mean, any research, be it basic research, be it applied research, we need to have a long-term orientation, long-term goal towards industry. And to survive the death valley of technology, we would like to propose a concept of technology integrator. Technology integrator is an entity who has both technical and financial capability to transform large-scale research to the industry, to the commercial. So they are able to talk about structure, electronic mobility, about the UV, about band gap, together with the researchers because they know about it, and they can do, they can plan the research together with researchers. And at the same time, they are able to make a financial projection for technology. So they can talk smoothly with financial institutions. This is what the technology integrator is for. Basically, it bridges the gap between the researchers and industry. These are typical challenges to commercialize technological patents or technology in general. The first one is no grand design, as I have mentioned earlier. Sometimes as researchers, we are too comfortable with ourselves. We are enjoying the research too much so that we forget that the research should bring benefit to the society. So sometimes researchers, especially in Indonesia, we don't have intention to level up the research. This is one condition that we have to admit and we have to solve. This kind of research results in non-productive technology or non-productive patent or publication. The second challenge is sometimes we have no commercial insight as a researcher. But I cannot blame researchers for not having commercial insight because the main job of a researcher is to do the research, to deal with the science. It's good to have commercial insight, but it's okay for not having commercial insight. That's why we need a technology integrator to give such insight to the researchers. And the third challenge is that sometimes the industry is unable to understand the technology because they don't want to deal with something complicated, something scientific. They just want everything practical. So because they don't understand the science, they don't want to understand the research, they don't want to give fund to develop the technology. And the fourth challenge is about the supply and demand, which is actually closely related with the timing. Sometimes we are developing a technology which is not there yet. I mean, the industry is not there yet. For example, I once had a research on the substoichiometric titanium oxide. This kind of material was invented like in 1950s, but revival of this material is only in the latest decade. And finally, in 2017, I guess, Toyota used this material for their new electric vehicle. So this is one of the examples that sometimes the time is not there yet. So it's quite difficult to develop technology. And speaking of developing the technology, we know that technology, the readiness of technology is measured by with a parameter called technology readiness level, or TRL. The TRL is divided into 9 levels, from level 1 to level 9. And we know that TRL level 9 is the highest. When the technology has achieved level 9, we consider that this technology is ready for commercial. It is already commercial production scale. But what I want to highlight is once we have a technology which already reached level 9, the TRL is already level 9, and we go to the bank and we ask them, hey bank, I want to build an industry using a technology. I already have a technology. of which TRL is already in level 9. Can you give me a loan to build this industry? And the bank will ask back to you, okay, you have a technology and readiness level is already 9, it's good. But have you implemented this technology somewhere else in a smaller scale, a commercial trial? Have you made a projection of the balance sheet or the cash flow based on this trial? What about the supply and demand? What about the supply chain? Those are the questions that will be asked by the bank or any financial institution when we bring a technology for commercialization. And this is because the financial institutions are thinking using a philosophy of commercial readiness index, or CRI. CRI is all about financial proposition. So what I want to emphasize that if we develop a technology, it's not only about the vertical integration, which is developing a technology from TRL level 1 to level 9. It's not about the lab work only. We need to think about the ecosystem. So the technology developer should think about the ecosystem of the technology. And this is why a technology integrator should not only work vertically, but also horizontally. By doing a horizontal integration means that the integrator integrates the technology developer with the financier, with the industry, and if possible, with support of government. If we have the support from the government, we have a strategic partnership which follows the concept of what we call a regulatory sandbox. Regulatory sandbox is a development of technology which is driven by the regulation from the government. It would be nice to have, but if we don't have a government, it's okay, as long as we have a powerful technology integrator. And this kind of partnership should be applied throughout the industrial chain so that we have the complete supply chain. We have the ecosystem, so we have no more issues in the bankability. We have no issues when we are facing with the financial institutions. So in summary, this is our proposal. There are 3 best friends: researcher, integrator, and commercial guides. So 10 years ago, there was a conversation between researcher and integrator. Researcher said, in the next 10 years, in the future, we would be needing energy storage. Energy storage is important, and tantalum is a very good candidate for the materials for the energy storage. The integrator said, because he knows about the industry, he have a long-term vision about what the industry would look like in the future. He agreed with the researcher. Yes, in the future, we will need many energy storage, but tantalum is not feasible. It's too risky to use tantalum because we don't have. Let's use something local for a secure supply and better feasibility. And this is what we call commercial insight. So we have the insight. I mean, the researchers have the insight from the integrator regarding the future commercial point. And researcher agreed with the suggestion from the integrator. Okay, let's go with carbon. Let's go with some materials which are cheaper. And the integrator will upscale the research and assess the financial performance in every stage of the development of the technology. So I would like to emphasize that financial performance is not only assessed at the end of the development, but in every stage of the development, from the research to the pilot, from pilot to the demonstration. We need to assess the financial performance in those stages. And 10 years later, these 2 best friends meet with the commercial guy, with the financial guy, and they have no, I mean, the financial guy, he has no objection with the proposal because this technology has been tested in the market. it shows a good financial and technical performance. So there's no boundaries, there's no obstacles to give fundings for large-scale production. So from here, we can see that the keywords are communication. And to be able to have a good communication, they have to have an equal partnership. And in order to be able to have an equal partnership, they have to have equal knowledge. So the integrator should put more investment on the human capital so that they can talk with the researchers and commercial guys smoothly. There should be more PhDs working in the industry, I'm going to say. So in the next slide, I would like to give you some examples on the ecosystem of renewable energy in Indonesia. The first example is the solar power, which has been, the technology has been elaborated deeply by Professor Wong earlier, but I would like to discuss about the ecosystem. So what Indonesia has in terms of the industrial ecosystem of solar power is only in the downstream of this industrial chain. We only have the fabrication and assembly and also the IPP, the individual power production. We don't have the upstream industry, whereas the upstream industries are technology rich. We don't have these industries because the first key issue is because of the market. The market penetration of solar power is very low. So there is no economic of scale. It's not feasible economically to build an advanced material industry, for example, because it costs, because we spend much. I mean, we spend more than what we gain from the investment. The market penetration is low because of the high electricity cost. The high electricity cost is because of the second key issue, which is the effectiveness of the technology itself. We know that the commercially available technology for the solar power currently is silicon-based, and it works, the efficiency is very low, and it works mainly based on the UV, I mean, it absorbs mainly the UV wavelength. And we know that in Indonesia, the effective or the average UV irradiation is only 4 hours per day. This makes the electricity cost very high. It is difficult for the time being for the solar power to overpower the cost of electricity resulted or produced by the coal-fired power plant. So it's difficult for the time being to reach the electricity cost as low as that of the coal-fired power plant, or PLTU in Indonesian. So this is another example that technology should be uniquely developed for a country. It would be nice if one day we will have a solar power which is activated under visible light, for example. The second example is the energy storage. Recently, Indonesia is very eager to develop the energy storage industry, but we still have so many key issues here. The first one is the technology readiness. We never do intensive development in the technology for the energy storage, not only for the battery, but also for the upstream industries, the mining industry. The motivation for us to develop the energy storage industry is to use local nickel. We recently realized that, oh, we have so many nickel, and nickel is used for the lithium battery, for the cathode, so we need to develop this. But we never actually developed the technology seriously in the last 2 decades. So the technology is still an issue. And the next issue is the capital support. Building the industry for the downstream of the nickel production is very costly. It takes around $1 trillion $1 billion to invest in the mining industry for the downstream of nickel production. And we also have the gap in the industry. The industrial chain is not yet established. So we need to do something for this matter, and regulatory sandbox is required in those two cases, for the solar power and for the energy storage. And in our company, we have sustainable energy goals. So we have a development plan in terms of investment and R&D. For example, we have a project on the development of biorefinery technology from palm empty fruit bunch. We are also engaged closely in the development of biofuels. If you have heard D100, we are closely engaged in the development of this technology. And we also develop the technology and investment for biomass power plant from either forest residue or from municipal solid waste. And also, we are going to complement what has been done by other state-owned enterprises and the government in the development of energy storage. This business is used to support our investment in the solar PV. How do we do that? We have three tools to do the integration. We have EPC competency. EPC is our core business. So we have the ability to upscale the process system from TRL1 to TRL9. And because EPC is our daily business, we have the ability to keep the expenses of the development low. And we also have R&D and investment to do the basic research, and also to invest to complement the industrial chain to create the demand, so that the technology will be feasible to be developed. And we hope by doing this, we will have someday an ecosystem of industry with added value economics as the focal point. This is one of the example of the concept that the integration concept that we have implemented. The first example is the biorefinery development. We started the development back then in 2013 together with Bandung Institute of Technology, or ITB, and we are currently in the pilot scale, and now we are collaborating with the government and with the producers of the palm oil company. And the second example is the green diesel development, the D100. The basic research was done by ITB since the basic research started in 2010. And now we are upscaling the technology, and we expect that we will be on stream on 2026. But we're not only developing the refinery process, but we also developing the upscaling process for the synthesis of the catalyst. So we did the basic engineering design, detailed engineering design, and EPC. And later on, we are going to invest some capital to expand the business for the catalyst plant as well. And for the next move is the energy storage initiative. We know that now we are developing the lithium battery, but I personally believe, as a researcher in the energy storage, I believe that the future energy storage should be beyond lithium battery. And we are doing the research and development focusing on the local resources other than lithium battery, because but the starting point will still be the lithium-ion battery. We know that the lithium battery, the components, some of the components are still imported from overseas. We need to do something to make it local. And as our strategy, we would like to develop the technology, especially in the mining industry, in the upstream, and in the advanced material. For the advanced materials, we are going to invest to secure the business as well, and we are going to create the demand by investing in the downstream of the industry, which is we want to create or we want to build a utility scale energy storage company for grid support, so that it will create the demand for the energy storage, so the industrial chain will be complete. So at the end of the day, we will have a real national energy storage industry. So that's the end of my presentation. And last but not least, I would like to invite you all to work together with us to develop local industry to build the industry together. So thank you very much. I will give the room back to the moderator. Thank you.
Thank you, Dr. Aditya, for an interesting research and technology transfer collaboration. And then, so to all honored keynote speakers, can you open up your mic and also camera so we can start our question and answers? Okay, so we have received like about 8 questions, and all of them has A, B, C, D like that. So hopefully all the speakers have time to answer all the questions. So this is the first question for Professor Robert. It is from Dr. Lucy. She wants to ask you about why we should concern with circular economy, and then how a circular economy can be achieved, and what is the time limit? What is the limit of circular economy model?
Okay, so why should we concern ourselves with the circular economy? It's basically most of the materials that we are using in our economy. Let's say we make a car, we are using iron, no? We are using copper for the motor, we are using aluminum for the engine, and so on. All of these materials are finite, limited, like our crude oil, coal, and gas, we know that. So sooner or later, we are going to run out of them in terms of extracting. So even, so we are going to run out of these materials. So it is important that we think of solutions where once we have made a car, once we have made a solar cell, once we have made any product that we have designed in such a way that at the end of its lifetime, it can be recycled back into its main components to make a new car, a new solar cell out of it. No? So to me, it's a matter of fact. No? We are running out of our materials. So that's why we need to look into a circular economy. How can it be achieved, right? For question 2. So we can start with policies. Okay, I've mentioned a few examples of green policies that the government and the parliament need to discuss, and if they are satisfied after deliberation, they need to start rolling them out so that industry and people have reference point and they know what to do, and it all makes also financial sense. Higher education institutes like Institut Bandung and here UNIKL and NTU and so on. We need to ensure that in our curriculum, we not only teach how to use, how to come up with some new process or modification, but we have to think what happens to our process at the end of its lifespan. Can this process, can this product be recycled with minimum effort, low cost? So right now, we are designing without the end in mind. So that's something we at the university also need to start changing when we teach. And then personally, we all need to look at our lifestyle and see whether we can make any improvements. Can we separate our waste? Some of us maybe have an opportunity to separate the kitchen waste, make compost out of it. I mean, this is something simple, can be done. Paper, plastic, metals, all of these packaging material can we separate and then return it back into a recycling center and get some money for it. Maybe now we don't get rich, so it's more a conviction thing, but that is a kind of lifestyle change that we can look at. Sharing cars.
I see.
And so on. And lastly, the limits, is it?
The limit of circular economy model.
Yeah, even though we implement all these policies and lifestyle and so on. Fact is that our recycling will not be perfect. So we will have impurities in our recycled material. And the removal of these impurities is very difficult. I mean, energetically, very difficult. So impurities may build up, and that affects the properties of our new product. Yeah? So that is an issue. And the other issue is that no matter what we do, there's always some losses, conversion losses. No? We are not converting a raw material 100% into a product. There are byproducts. That is during the manufacturing. When we are using equipment, there are also losses. Imagine a car running on tires. You buy a new tire, the profile is a few millimeters thick. After you have driven the car for maybe 50,000 kilometers, the profile is gone. Your rubber particles are now dispersed on the road. No one is collecting these rubber particles back, right? Same goes for metals. Because of corrosion and wear and tear, friction, we are losing metals. Prof. Lydia mentioned iron oxide, the rust. No? So we are losing material because of these natural processes. So over time, our stock of material is going to shrink. It is going to become less and less and less. Maybe we are talking about a time frame of 1,000 years and 10,000 years. So right now, maybe that is something, it's not immediate danger. COVID-19 is an immediate danger that we have to handle. But philosophically, long-term, strategy-wise, visionary, we have to think about that. No? And the limitations are that sooner or later, all our material that we use to make cars, houses, solar cells are finished. And I've mentioned that at the end of my slide, some new idea where people look into space, sending rockets to asteroids and bring rare earth elements and other metals back to Earth to compensate for the losses. But even that, I don't know whether it is still economical and meaningful.
Okay.
I hope I have answered Dr. Lydia's question, Dr. Lucy's question.
Yes, I think it is answering, Professor. So let's move to, thank you for the answer, Professor Robert. Let's move to the next question. It is for Professor Lydia. Thank you for your interesting presentation. It is also a question from Dr. Lucy. First question is, do solar energy systems need a lot of maintenance? And the second question is, how much will a solar PV system cost in general? And how long will it take for it to pay for itself through energy cost savings? Thank you. Can you get the
Okay,
question?
thank you for the question.
Okay.
Yes. All right, so thank you for the question. So to answer the first question, whether solar energy system needs a lot of maintenance, the answer is not really. In fact, if you buy a solar panel, the warranty is for 20 years. And we have done some calculation in terms of cost and time for break even, considering Singapore price of electricity. For a typical landed house in Singapore, where we can install the solar panels on the rooftop, it will probably take between 5 to 7 years to break even. And that is a very conventional calculation, very traditional. So which means after 5 years, you will earn back the money you invest in solar panels. And for the rest 15 years, you almost pay nothing for your electricity. I think that's based on our calculation in Singapore. The cost of the solar panels itself actually consists of two main elements. Around 50%, 40 to 50% is the solar panel price, which usually you can purchase from a lot of manufacturers based in China, and the cost has been decreasing tremendously. And the remaining 40-50% is on the installation, is on the packaging, the installation with the AC/DC converter, the battery, and the installation on the rooftop. So I guess the second part of the cost may still be can still be reduced depending on which country you are deploying it, right? For example, the labor cost in Indonesia and the labor cost in Singapore is different. So there is a potential cost saving there when you install and assemble solar panels in Indonesia or China versus Singapore or Europe. How long will it take for it to break even? I guess we still have to do the calculation based on the cost of electricity in a particular country, and then compare it with the amount of sunlight that is generated in that country. So Singapore and Indonesia and Malaysia are probably very similar profile. But if you do this in Australia or in Europe, is a totally different story. Summer and winter, you will have different amount of energy as well. But to answer the question briefly, right? I think with the decreasing price of solar panels in the past 5 years, I think it is very appealing now to install solar panels, not only in the cities area, but I think especially in Indonesia, where you have thousands of remote islands where you cannot actually connect them with grid electricity, the benefit of solar panels actually far outweigh the cost concerns, because with electricity you actually improve the quality of life of a lot of people in the rural area and also on the islands. But I guess this is something that I hope the Indonesian government will do a more active role. I know a couple of collaborators who has projects in installing solar panels in Papua, and you cannot imagine how much they spend just on the transportation. Yeah. It is probably a few times more expensive than the solar panel itself. So I think it's a pity that this cost factor limit the utilization of solar panels in the remote areas in Indonesia. Yeah.
Thank you for the answer and insight, Professor Lydia. Another question for you. It is from Mr. Ricky. The current condition of solar cells, an enormous amount of energy produced from sunlight makes solar cell a promising alternative. But is there another support system needed to store the electrical energy generated so that the output can be more stable and can be useful even there is no sunlight at night?
Okay, so most of the solar panels installed require a battery system. So there's always be whatever energy whatever electricity that you produce in the daytime will be stored. If it is not used directly, it will be stored as a battery and used in the nighttime. Yeah.
Okay, thank you. And here is the question to Professor Robert again from Eka Masrifatus Anifa. What is the role of industry in the circular economy to maintain a sustainable environment, such as extended producer responsibility? Okay.
Yeah, the role of
industry.
The role of the industry in a circular economy. Try to be responsible from the off when you come up with products and services. Have the end in mind. No? So it's not just about selling it and then leave the user alone. No? Provide after-sales service. Make sure your product can last. So it's not so much focusing on sales, but on services after you have sold the car. Like for cars, we have service centers. We bring our car every 10,000 kilometers to the center to make sure everything is in good shape. And that has to be the thought for basically all products that we don't eat. Washing machines and TVs and so on. And the industry also needs to provide consumers with the opportunity to return broken products back to them. Yeah, so if we do not have that opportunity, we may just end up throwing this material into the waste bin and it goes into landfill. And then we are still at a linear economy. No?
I see.
So there are many things that the industry needs to do in terms of R&D, in terms of marketing, after sales, and in terms of developing recycling solutions for the product at the end of the life.
Okay.
I hope I could answer the question.
Thank you, Professor Robert. I think it's quite interesting for the circular recycling system for the industry. Okay, I think we can move to Dr. Aditya. It's your time to answer the questions. So it is from Michael Dega. It is about how is the progress of the research in Indonesia, especially for the new energy application. And then we can combine with Dr. Lucy question here. Pay particular attention to the evolving institutional relationship between academia, research, and industry. How would PT Rekayasa Industri build this relationship so far, and what kind of collaboration that was done? Can you get the question?
Yes,
Dr.
I guess.
Aditya? Okay.
Thank you for the question. For the condition of the research and development in terms of the renewable energy in Indonesia, most of the research is still in the lab scale. So that's why what we are doing now is we try to incubate those research upscaled to the higher scale to be ready for the commercial scale. That's what we've been doing in our company recently. But actually, in Rekayasa Industri, we have built such good relationship with academics for a long time. But previously, our relationship was only we collaborated to solve some industrial problems. But recently, we started to be more serious in incubating the technology. So we started the research together, or we upscale the technology that has been developed by the research institutes or universities, or we invest some money to the startup, to some tech startup, so that they can expand the business as well as the technology, of course. And if I may, I would like to add some answers to previous question from Dr. Lucy. So the cost of the solar power, the utility scale solar power in Indonesia, the rule of thumb is approximately $880,000 per megawatt. This is for the utility scale, not for the rooftop. But according to our experience, we can suppress this price to as low as around 500 to 600 only for the solar panel. For the installation, it will be higher than that, and it still excludes the battery. The battery cost is also very high. And also another problem for implementing the solar power in Indonesia is about the land. As a rule of thumb, for the utility scale solar power, we need 1 hectare for every 1 megawatt generated. So we can imagine for the big cities like Jakarta, it will be very difficult to find such land. So the research such as transparent solar panel will be very good for the big cities. So I guess that's all.
Okay, thank you. So another question, let me see the list of the question first. It is from Dr. Oh, wait a moment. My computer is stuck. But if Dr. Purwanto is here, maybe you can open up your mic and and give your question. Oh, wait, here. So, wait a moment. I'm sorry. Oh, here. For Professor Lydia, it is from Dr. Moh Purwanto. The question is about what is the best design for high energy production from a solar cell? For example, spot position, tilt angle, or etc. The second is, what is the role of doping and catalyst in the solar cell process? And the third question is, how to manage efficiency of solar cell performance?
Okay, thank you for the question. I did not cover this in my talk, but I think it's a very relevant question. To ensure the optimum amount of sunlight falling onto the solar panels, we need to take into consideration the latitude of the Earth. For example, so that there is a calculation which can be used to calculate what is the best tilt angle of your solar panel. So for example, a country in the equator like Indonesia or Malaysia probably only need between 5 to 10 degree C of tilting. But a country in the northern hemisphere, maybe in Japan or in Europe, you probably need a slightly higher tilt, like 20 or 30 degrees C, to make sure that the sunlight will directly hit the solar panels at the favorable angle. The second question is on the role of doping and catalyst in the solar cell process. Basically, in solar cell, your main purpose is try to optimize the amount of photons absorbed. That's number one. The second one is to make sure that the amount of electron and holes generated be harvested as much as possible at both electrodes. In other words, you need to make sure that the electrical carriers transport very smoothly. And doping and catalysts help this process of electron or hole transport. I hope I answer your question in a very simple way. I actually give a one semester course based on this, so it's not a very easy. It's not something that I can answer in 2 minutes.
Exactly.
And how to manage efficiency of solar cell performance? I think we can do it generally in two big way. One is the solar cell itself must be designed in such a way to give the highest efficiency possible. So the techniques that I discussed just now are the techniques used to improve the power conversion efficiency of the solar panels itself. So once we achieve this by doing either catalyst or doping or cation substitution or changing of the interfaces, once we have the optimum power conversion efficiency of the solar panels, and then in the installation part, you have to consider factors like the tilt angle and also the amount of direct sunlight that you obtain. For example, in the equator, in Singapore, for example, we have a lot of clouds. So the amount of direct sunlight that we obtain is actually less than during summer in Europe, where they actually don't have so much cloud. So we have a lot of diffuse light in humid countries because of the clouds. So because of this, we can implement different types of optical enhancement strategies. So this is another topic where we can enhance the efficiency of solar cell. Yeah, so I hope I answered the question.
Okay, thank you, Prof. Lydia. And this is about, I think, one more question from Dr. Lucy and from our chairman. It is about like, what is the current research that all the keynote speakers have been done till now? So maybe it is about an inviting collaboration that we can make in the future. So maybe you can like give some brief explanation about your current research. So maybe in the future we can have the collaboration. Maybe Professor Lydia first.
I think I have explained briefly what kind of research I've been doing. So mainly in the fabrication of materials for solar panels and as well as for artificial photosynthesis. I have collaborations with a couple of universities in Indonesia. At the moment, mainly still in Java, like ITB and UI, ITS. The kind of collaborations that we did is usually the Indonesian partners maybe looking into ways to synthesize new materials, because this is something that they can do easily in their chemistry labs. And we can help in doing advanced characterization. So they can actually send samples to us, and then we can try to help to understand the properties of these new materials. Yeah, so I'll be happy to explore new ways of collaboration with ITK as well.
Okay, thank you, Prof. Lydia. And what about Prof. Robert? Is there any opportunity?
I'm working with the palm oil industry quite closely. I have a collaborator in the Malaysian Palm Oil Board, MPOB. And one project is where we take the byproduct from the refinery, the spent bleaching earth, remove the oil, which is already done commercially, and use the de-oiled spent bleaching earth to recover nutrients from the palm oil mill effluent. Then collect our de-oiled spent bleaching earth with the recovered nutrients and add it to soil and see how plants respond to this soil modification involving spent bleaching earth and recovered nutrients. So we kind of try to close some, not all, but close some material loops for the palm oil industry. So that could be an area of collaboration with Ithaca.
Okay.
Closing loops in the palm oil industry.
Okay. Thank you, Prof. Robert. And then it's time for Dr. Aditya. And I will highlight the question again. And what kind of collaboration can be done in the future with academia or researchers instead of only internship program with your company?
Okay, maybe for the first question, what we are doing in the company right now is besides the biorefinery and also green diesel and green after development, we are also developing the technology for biomass conversion to power. The biomass could be from the forest residue, the palm oil fruit bunch, and as well as the municipal solid waste. This is a part of the co-firing project of the government as well. And we are also initiating the development for lithium battery anode material. And it will be happy. We would be happy if we can collaborate with any of you. And as a researcher myself, I personally, outside the company, I also do some research on the photocatalyst, especially in the development of substoichiometric oxide catalyst for CO2 reduction and for water treatment. So I personally would be happy to collaborate with other researchers on this. And speaking of the collaboration between our company and academics, as I have mentioned earlier, we are focusing on the incubating the technology, incubating the research towards industrialized or commercial scale technology. So an internship is an old school style of collaboration. So we still do internship, but we focus more on the technology right now.
Okay.
Thank you.
Thank you for the answers. So for all attendees, if you still have questions, you can just directly ask by open your mic. I will wait for about like 1 minute if there's one of you want to ask. because
while waiting for people. Okay, instead of just saying we can collaborate, I want to also share an example of how UniQL supports collaboration.
Oh, nice.
For example, with MPOB, we have a collaborative research grant scheme that is CRGS. And what we do is those partners, they pledge a certain amount of money, can be real or not real money, that we put into a project. Let's say UniKL puts 20,000 ringgit in and Ithaca puts 20,000 ringgit in. And the partners will be responsible for delivering certain aspects of the research portfolio within their institute. So the money does not need to be real. No? Let's say when you analyze a sample, if you would send that sample outside, you would have to pay money. So you can say one sample costs 100 ringgit. You analyze 10 samples, this is 1,000 ringgit, isn't it? Labor cost, we can also factor in. So this collaborative research grant scheme is something that could be looked
good.
at.
Yes, okay. Thank you, Prof. Robert. I think there's no more question from the attendees. And thank you for Prof. Robert, Prof. Lydia, and Dr. Aditya for the explanation and the answers. So let me summarize our today's plenary session discussion. It is a very interesting speech from Professor Robert that we can learn about a transition from non-renewable everyday goods to a renewable one may convert the current linear business model into a circular economy, which is required a concerted global effort for all members of the society. And also, even though it is very good to be done in the future, but it is not completely stop the loss of materials. So that's why we need to think a new solutions of it. And while in in Professor Lydia's speech, we understand that solar cell need to be explored way beyond of only just use silicon due to the lack of space of the rooftop solar. And then a more advanced technology involving new materials, novel processing and fabrication techniques are required. And then to accommodate the innovation that we need, a printable semiconductor to get artificial photosynthesis is very interesting. And then we can also take benefit of hematite, iron oxide, into a solar water splitting, which is very also interesting for me to hear it today. And furthermore, a nice presentation from Dr. Aditya is about technology ownership is essential for a successful development of a country, but the transfer of this technology, I mean, from the research to a commercial stage is a very big homework that we have done yet. And researchers and industrial practitioners in which inhibit the communication, research, quality, and vision, and also commitment are required. So thank you for all the explanation. And also we received many ambitious questions from attendee about the concern of circular economy, role of industry in circular economy, the technical, explanation about the solar PV development and innovation, and also an opportunity with Rekayasa Industry Company to have the collaborations. And from all the keynote speakers, we also got some opportunity of research collaboration in the future. And my closing statement is like, what we need to get all knowledge implemented well in the real world, we need to have a good partnership between researcher, circular economy, and also a technology integrator to implement what we research in the real world. So thank you for the keynote speakers and attendee. It is a fruitful discussion. Hopefully we can get insights and ideas that can be useful for the future. But unfortunately, my time has come to an end as the moderator of this plenary session. So thank you for listening and give a good cooperation. I would like to return my session to Miss Susan as the Master of Ceremony. Miss Susan, are you
Thank
available
you,
there?
Dr. Happy.
Okay.
Yes. Thank you. That was wonderful discussion session, Dr. Happy Aprilia. We're so thankful for your conduct today, and I hope that all the participants were enjoying. If you have any more questions, maybe we can have another discussion in parallel session as well as in during the break time. And let's go to the next agenda. Before we go to parallel session, ladies and gentlemen, I would like to invite Ibu Elin Diasa Fitri because we're going to have giving the award certificate for the keynote speakers and our lovely moderator today. So Ibu Elin, are you there? Yeah. So I would like to give the time to Ibu Elin. Time's yours, Ibu.
Thank you, Miss Susan. We are so grateful for the elaborate research and discussion presented by the keynote during this plenary session. Therefore, I, on behalf of the organizing committee, would like give award certificate to keynote as well as to the moderator for conducting insightful discussion today. First, for Prof. Robert, thank you, Prof. Robert, for the sharing knowledge. And the second, for Dr. Aditya Farhan Arif. Thank you, Dr. Aditya. Next, for Prof. Lydia Helena Wong. Thank you, Prof. Lydia. And last not but the least, for Miss Happy Aprilia as moderator. Thank you, Miss Happy. Thank you. I will return back to Miss Sun.
Okay, thank you, Bu Elin. That was all the word for the keynote speakers and the moderators. Before we continue to the parallel session, I would like to give some information. So make sure that every participant has already put the room for you to present your materials, as well as the invitees and attendees. If you are looking forward to get into the room, you need to put the room number, in order the committees put you there as soon as possible. All right. I would like to say hi to all participants here from the neighboring campus here from STT Migas, representative from STT Migas. Bapak, are you there, Ibu? No one? Okay, some of our participants delivering their asynchronous material, so maybe at the last minute or a few days before, they have been changed into asynchronous, so they are not able and willing to open the camera and attending this conference live. So next, probably Polytechnic Balikpapan. Bapak Ibu, are you there? Let me check the name first. If I can recognize one, then I will just. Oh, seems no one. Okay. All right. Before we continue, I would like to also introduce the member of the committees. So this is very important, Bapak Ibu, because this conference is the result of the long work and collaborative, iterative process that involve a lot of people, especially the lecturers of Institut Teknologi Kalimantan. So probably I would like to share some screen about the members of the committee. Okay, so here we are. Sorry. Okay. So we're going to have this, Bapak Ibu. Our General Chairman is Ibu Elindia Savitri. And then the steering committees, Professor Insinyur Budi Santosa, Ibu Nurul, and Dr. Muhammad Mazhuri, Dr. Muhammad Purwanto, and Secretary is Mr. Bima Catur Apriyadi. Our treasurer for the BICAME 3 is Ibu Kamilina Rodia. And all of us here supporting the conference, starting from Dr. Eng, Ibu Lucy. So we usually call her as Bu Eng, something like that. She's one of the most wonderful people in ITK and we adore her. Ibu Lucy, hi, are you there? Please open your camera.
Hi, Bu Susan.
Hi.
Great to meet you virtually.
Yes, thank you. Where are you now? Where are you streaming online?
I'm home.
You're home?
I'm home.
Okay. All right. Did you find any difficulties connecting to us today in the morning?
Not really, but my network connection is a little bit unstable. So
okay.
Sometimes I turn on, sometimes I turn off.
All right. Thank you, Bu Lucy, for actually conducting this together with our members. Well, then followed by Ibu Nadia Almira Jordan. Ibu, hi. Bu Almira Jordan, are you there? Okay. Maybe she is in the process of running around somewhere. Thank you, Bu Nadia. Bu Win. Hello, Bu Win. How are you today?
Oh, thank you.
How's your feeling preparing all of these things? Did you have any problem or obstacles during collecting the papers, organizing the reviewers? Bu Win, what do you think about your preparation with your team? Win? Win, are you staying there? Okay. Well, next, Ibu Intan. Ibu Intan, hi. How are you today?
Good. Hi, Miss
Okay.
Susan. Hello.
So, how is it? You're working with your team. Is there any problem with our preparation? Is everything going well?
Yes, I think everything is going well.
So, where are you streaming online from?
From home in Sidoarjo.
Sidoarjo, okay. Thank you, Bu Intan. Mr. Muhammad Chandra Cahyo Tomo, are you there? Say hi, please. Okay, I think.
Yes, I'm there.
Oh, yeah, you're there. Okay, good. So he is one of the key persons presenting this kind of conference, taking care of the technologies and support system here, as well as to Mr. Gilfi. So how is your feeling today? What do you think? Finally, this happened.
Interesting.
Interesting. Okay. This is your first conference committee, or you have been like doing this for several times in a different conference?
Yes, I'm in the campus. I'm online from the campus.
Okay. All right. Thank you, Mr. Chandra. All right. And then we also have Mr. Nurfajri Azhar. Would you mind saying hi to all of us? Okay. He seems offline. And then Mr. Shalam. Yeah, Mr. Salam. I know you and I'm familiar with you. So how's it going there? Mr. Salam, would you mind saying hi to all of us?
Yeah, Bu. Yes, Miss.
Okay. So what is your job description in this committee, Mr. Salam? Do you find any interesting things during your work, collaborative working with your team?
I am supporting Mr. Andrew.
Okay. All right.
Because Mr. Andrew is my manager in
Oh,
this
your manager.
technical committee.
Technical committees. Okay. Yes. Thank you, Mr. Salam. Mr. Samsul, are you there?
Kalau misalnya pengujiannya seperti ada SEM dan
Okay, how are you, Mr. Samsul?
Alhamdulillah fine.
Okay, so what do you think about this conference today? The preparation.
Alhamdulillah going very well. I'm organizing on SECL for collecting the paper from the author.
Selecting from the authors. Okay. Yeah. It was a great. Thank you. Finally, yeah. Okay.
Welcome.
Next. Thank you, Mr. Samsul. Mr. Ainun. Okay, Mr. Ainun, are you there? Mr. Ainun is one of the most workaholic members in this team, instead of those people who are so motivated. So come on, Mr. Ainun, come up with your camera, share your stories about how you prepare this event. All right, you seem to be offline. Okay, let's just welcome Ibu Diniar. Okay, Ibu Diniar. She's my favorite, ladies and gentlemen. She's one of the old member of LPPM who is holding a conference before, like Econis. So, Ibu Diniar, are you there? Would you mind to open your camera?
Yeah, Mrs. San.
How are
Hello,
you
everyone.
today?
I feel so good today.
Okay, good. So, how is it going? The preparation until the event today.
During the preparation until the day of BICAME today, I think runs so very well. Thank you, Mrs. San, for conduct this conference very well, and thank you so much for Mr. Prof. Robert Bachman, and then Prof. Lydia Helena Wong, and Dr. Aditya Farhan Arif for joining us today. Thank you, and for all the participants, we will back to the panel session.
Okay. Oh, not yet, Bu. We still have some members.
Oh yeah. Okay.
All right, we're going to keep going until the last member, because this is the time for us, yeah, for showing our work together finally. All right, Ibu Diniar, thank you so much.
Thank you, Mrs. San.
Yes. Let's go to Mr. Andromeda. How are you there, Mr. Andromeda?
Hello, Miss Susan. I'm
Hi.
fine, thank you.
Yeah, how are you today?
I'm very fine, thank you.
Okay, so how's your work going with the conference?
Yeah, I think this conference is very amazing. The papers have a good quality, and we hope all of papers can publish in Scopus Index.
Okay, thanks God, yeah. It will be such a wonderful work for all of us finally publishing all the materials papers in the Scopus. Thank you, good job, Mr. Andromeda.
You're welcome.
Thank you so much. Miss Anissa Ramita, are you here? Miss Anissa? Okay, she seems offline probably. Let's go to Mr. Gilfi Langgawan. Okay, he's one of the most important person today in this meeting in conference. He's preparing for everything together with Mr. Cahyo for the supporting IT support. Okay, Mr. Gilfi, would you mind to open your camera and say hi to all of us?
Hello for that.
Yeah, good morning. Oh, Mr. Gilfi, you are wearing a mask.
Yes.
So where are you from? Streaming online from?
From office.
Office, okay, fine. So you were wearing mask to obey with the protocol, something like that?
Yes, because there's all people in here, so I cover my face with mask.
All right. Okay, thank you. Thank you for the good word, Mr. Gilfi. Finally, Mr. Trisnadi Bagus Arifianto. Are you there, Mr. Trisnadi? Okay. He seems offline. All right. Bapak Ibu, I will also introduce the scientific committee, but since they are in a different time zone, in a different place, so here we are. Ada Ibu Lu Putri Adyani, so there is Ibu Lu. She is currently in Australia taking for the postdoc program, doctorate program. And Mr. Adiansa, Mr. Ricky, Miss Yunita, Miss Happy, who is actually our moderator today, Miss Cut Kamala Banaget, Mr. Torikul Huda, Mr. Yan Deni, Mr. Adi Mahmud, Mr. Theodora Astarga Amatosa, Ibu Handrianti Dia Puspita Rini, and Ibu Ilma, Ibu Julian, Dr. Insinyur Isna, Bapak Subhan. Bapak Subhan is our prior Vice Rector of Academic Affairs, Dr. Suhartono, Mr. Bima Prihasto, Mr. Ahmad Aris Pratomo, Mr. Pandisya, and Dr. Mardija, Dr. Insinyur, Dr. Ing Victor Yuardi. Okay, those are our scientific committees. All right, going back to our agenda today, ladies and gentlemen. We're going to go to parallel session. So before parallel session, I just want to make sure that everyone has already put number on the room. So we're going to have some videos first while we are waiting for the breakout room starting. Okay, Mr. Committee, Mr. Gilfi, maybe you can just put and play some of the videos related to our activities during the preparation, or maybe actually the review or the activities in ITK, Institute Teknologi Kalimantan, before breakout rooms begins. Okay, ladies and gentlemen, I would like to a little bit review about the rooms, our rooms today. So the first room will be about the energy conversion, energy storage, technologies, and renewable energy. That is our actually plenary. And then the second room will be environmental sustainability, land and water resource engineering, building and landscape, smart automatic system, sustainable rural urban planning. And then the room 3, it is containing about agricultural informatics, bioinstrumentation and control, green vessels manufacturing, cost and energy efficiency of autonomous vessels, and on marine industry, offshore energy infrastructure and market, methodologies and tools for secure operation and control of smart energy systems. And then room 4, we'll talk about applied mathematics, computational science, mathematical physics. So other participants, you can join with the rooms you are intended to attend. Yeah. Guests as well, welcome for just put the room in front of your name so the committee will get easily to recognize you. Okay, so Bapak Ibu, all other participants, maybe you are streaming from YouTube, you can join with us in a breakout room. So just get into our links in Zoom room. We are going to have break time until 1 p.m. So while then, you may join the breakout room, as well as having the breakout time for lunch and other activities before we start and begin the parallel session.
Susan, Robert here.
Yes.
Susan, how do I join the breakout room? Do I need to receive a link, or in Zoom there is somewhere I need to click? Sorry, I'm not the most expert in this. I know how to use it for presentation, but to switch to rooms, I am not so expert.
Okay, Professor, you need to put the room you're intended to attend and in front of your name, in front of your Zoom ID. We're going to put you into the room. The committee will put you in the breakout room while we are waiting for him to arrange the room for all of us. So
the
we're
Zoom
just
ID.
Yes, your name. So you rename through
okay.
the top right button there. Yeah.
So let's say my room ID.
Yes, exactly. You can rename there.
Is...
We are still waiting for the committees to put us in a breakout room. Mr. Gilfi, I think we need to put them into breakout room as possible. What do you think? Because the parallel session is beginning. Oh, I'm so sorry. So, ladies and gentlemen, we don't have any time for lunch or coffee breakfast. So we are going to directly put you in a breakout room.